Hey guys, good evening all of you. Very good evening to all of you. And I'm sorry to keep you guys waiting. Yeah. So let's get started. I think let's get started. So today's session will be on logistic regression, and it's a very interesting topic. So what we'll be doing is we'll be spending a little bit of time understanding some of the theoretical aspects behind what logistic is. It's a bit of a difficult topic in a way. So not like linear regression, but logistic is a slightly different topic. So we'll be looking at some of the theoretical nuances, some of the conceptual nuances behind what logistic is, and from there we'll be getting back to some of the specific code demos and some of the specific code hands-on. And once again, as usual, I'll try to focus more on the hands-on side of things, the practical side of things, how to actually do logistic regression. Okay, so we'll be looking at that aspect more than just bore you with theory, right? So, but yeah, so that's pretty much how we'll pace the class. We've got a good 1.5 hours with us, and so let's get started and let's get going. Okay, yeah. What about linear regression? Linear regression is not today's class, right? Is it linear regression? Okay, so it's not linear regression. It's logistic regression we are looking at. Yeah, it's not linear. Yeah. Okay, the guys, the session is on logistic. It's regularization on logistic. So we'll be looking at that aspect. Yes. Yeah. No, so regression, see, the concept of regularization is very similar, right? So you have to understand the concept of regularization is actually, yeah, it is a different session. Okay, so let's not confuse into all that, right? Let's get started, like, let's get started. Let's not waste time on all that right now. Yeah, so basically, again, what I want to do is focus more on the practical aspect of things, right? So there's a lot of theory that you have around it, but we want to focus more on the practical side of things. So let's get started, all of you. So before getting any further, what do you mean by logistic, and what are some of the aspects that we have around logistic regression, and how is logistic different from linear regression? When we talk about logistic regression, how is logistic regression inherently different from linear models? What is the similarity and what is the difference between basic logistic regression model and a linear regression model? So let's quickly take a look at that aspect as we get going. All right. So so what we have is in a normal linear regression situation. In a normal linear regression situation, we have this, right? We basically have a situation like this, where in a normal linear regression situation, we have a situation where region lasso, is it? Okay. Okay. Yeah. So regularization is with respect to, guys, logistic regression is basically the thing. I think there's got to be some confusion with you guys. Yeah. Okay. So we'll get on with that. Hold on, guys. Let's not waste time on that right now. We'll get on with that. Some of you have already studied. I think let's not waste time on that, please. I think we'll carry on with the class, and I think we'll come back to some of those things in a while. Okay. Yeah. Let's not get into all that right now. Okay. Just to quickly recap the quick piece as to what linear regression is. So in linear regression, what you're trying to do is you are trying to go ahead and you are trying to predict y from a given x, right? You are trying to predict a specific y from a given x. That's what you're trying to achieve in linear regression. It could be a line, it could be a curve, it could be basically about anything. That's what you're generally trying to achieve with respect to normal regression model. Now, how is logistic different? How is logistic regression fundamentally different with respect to linear? Logistic regression is different because of this specific reason. Here, from a particular value of x, you are trying to predict a probability of y. So here, from a x, you are trying to predict the value of y, whereas in logistic regression, fundamentally what you are trying to do, from a particular value of x, you are trying to predict the probability of y. Okay, so I think that's one aspect that is important to understand. Now Now coming back to the idea, of what is and how is it different. Exactly. So let's take a simple use case. Let's take a simple use case of this thing. Let's say we have got a scenario where we have salary and we have got, let's say we've got salary and we have got the default rate of a person, right? We've got salary and we've got default rate of a person. These are the two basic features we've got, right? Now salary of the person can be, let's say the salary of this is basically part of your label data. Right? So what we have got right now is part of your label data. So given the salary, you're trying to predict defaults in a way, right? So salary is, let's say, 10 and default is, let's say, equal to 0. Salary is equal to, or let's say you're trying to predict loan repay. Let's just change this thing for a second. Let's say you're trying to predict loan repay. So given the salary of a person, you are trying to predict whether the person will repay the loan or not. That is the prediction you're trying to do. Given the salary of a person, you are trying to predict whether the person will repay the loan or not. Okay. So salary is 10, repay is equal to, let's say equal to let's say 0, and when salary is equal to 30, repay is equal to 1. That means if your salary is high, you're repaying the loan. This is historical data that you're collecting. So the labeled historical data that you're collecting. Let's say salary is equal to 50 and repay is equal to 1, and salary is equal to, let's say, 15 and repay equal to 0, and so on and so forth. This is the historical data you've got right now. So what we are doing here, just to help you visually understand this thing, and see, this is the general thing that happens. Everybody knows Logistic, but generally the intuition is something nobody understands. Like, that's a reality. Okay, so normally the way we study things, we end up memorizing formulas, but not many of us understand the intuition behind how it happens. Okay? That's the whole idea behind looking at this, slightly different light. And once you understand this thing, the extensions are actually very, very easy. So now let me represent this data. Let me quickly visualize this data here. So if you visualize the data here, if your salary value is less, that's your salary and that's your probability of repay. So that's your salary along the x-axis. That's your salary along the x-axis, and along the y-axis you've got probability of repay. So that's what we have got right now. So given your salary values are equal to, let's say, low, if your salary values are low, the repay value is equal to less. And if your salary values are high, the repay value is equal to 1. This is what we have got right now. Simply this is what we have got right now. So salary value is 0, salary is low, the repay value is equal to 0. And as your salary increases, as your salary value is high, the repay value is equal to 1. That's effectively what we have got right now. Okay, now coming back to how do we model this thing? This is my labeled historical data. So what you've got right now is your labeled historical data. So how do we model this thing? How do we go back and effectively do a modeling for this specific thing? How do we model this thing? So what we are trying to do is we are trying to fit a line, or we are trying to fit a model that best fits the point. Like, what is the line or the curve of best fit? That's what we are trying to achieve right now. Okay, so how do we find a line or model of best fit? So one of the simple ways to do it would be, we can draw a regression line that best fits the point. In fact, that's the fundamental inspiration behind Logistic. The Logistic regression is a follow-up of linear regression. It's basically a cousin of linear regression because of this specific reason. So ultimately what you're trying to do is, given salary and repay combinations, you're trying to build a model that best fits the points. You are trying to effectively model the relationship between salary and repay. That is what you're trying to achieve right now. You are trying to find the relationship between salary and repay. This is the relationship you're trying to learn right now. Salary, repay, what is the relationship? Now the thing is, but you cannot have a regression line that you can learn like this, can you? You cannot learn a regression line like this. How can you learn a regression line like this? I'll tell you why you cannot learn a regression line like this. The problem is, in linear regression session, and guys, just to in linear regression session, we have learned that if you have to make predictions with respect to this line, how will you make predictions? If your salary value is high, the probability of repay will be very high. And if your salary value is low, the probability of repay will be very low. It can be more than 1, it can be less than 0. The values can be higher than +1, the values can be less than 0. Both the possibilities are there. So how do we practically model it? How do we practically go back and model this thing? How do we do it? So what we do is we have to figure out some way to flatten this curve, right? We have to flatten this curve right now. This is what we have to achieve. We cannot have a regression line to model this thing. We have to somehow figure out a way to flatten this curve. And this is the inspiration behind the sigmoid curve. So in linear regression, what we try to do is using salary, we try to find the best fit line that fits to the point. In logistic, what you try to do is, on the contrary, in logistic, what you're trying to achieve is you are trying to find out, hey, what is the sigmoid curve that best fits the classes, that best fits these points. If I just take a slightly different viewpoint, what you're trying to do is you are trying to learn, hey, what is this best fit curve? This is the distribution of my data points right now. The green points are here, the red points are here. In case you're wondering what is the green is basically repay equal to 1. If repay is equal to 1, probability of repay is 100%. And if repay equal to 0, probability of repay equal to 0%. That is the distribution of your data you have got right now. And on this, what you're trying to do is you're trying to fit a sigmoid curve or an S curve that best fits the points. That is what you're trying to achieve right now. So how should you space this curve? Should I tilt it a bit like this? Should I tilt it a bit like this? Should I place it a bit on this side? How should I find out a sigmoid curve of best fit? That's how logistic regression is different from linear regression. Fundamentally, in both the cases, you are trying to learn something. You're trying to learn a line or a curve or a function, something. In logistic, you are trying to learn a best fit sigmoid function. In linear regression, you are trying to learn a best fit line. So the output was basically y in linear regression. Linear regression, the output was basically y. That's a feature you are trying to predict. This output was y. Whereas in logistic regression, the output is basically the probability of y. So probability of repay. What is the probability of repay? Okay, so this is effectively what we have. And finally, what is the equation of this? What is the equation of the sigmoid function, which all of you have gone through? Just wanted to quickly recap it for everybody once again. And guys, see, one thing I want to absolutely clarify. See, I don't know if you have seen. I think we have met a couple of times, 1 or 2 times. See, my sessions are very different. Okay? I will not rush to the topics. See, I know your topic is regularization, linear, and I will do 1 more session, 3 more sessions. How many sessions you need? But what I don't do in classes is just come to a topic, do the topic, and leave. That's not how I teach. Okay, so just to clarify, absolutely to allay your concerns, so we will look at it end to end. So please don't worry. Okay, so in just in case today time is limited, we will look at use cases, because see, regularization is not like one topic that you come and you read from 10 slides and you complete. That's pretty much the experience probably most of you would have had. But basically, regularization is a very deep topic. Right? So you cannot understand regularization if you don't know logistic. And because you studied this long time back, it's important to understand this. And this is not only for 1 or 2 people. 1 or 2 people, you might be sharp, you might have studied. It is for the entire most of you, right? That's an important aspect to keep in mind. Okay, so just don't worry. So just in case, see, just to clarify, Elastic Net also, if you want a separate thing for that, we will do 1 more, and I'll talk to the team and we'll organize 1 more session, 1 meeting. Okay, we'll discuss that in detail. Elastic Net, ridge regression, lasso regression. Okay, so we'll talk about that. Regularization, we can do 1 more entire theoretical session on that thing. But you cannot understand specifically logistic and other things without even understanding what is a sigmoid function. Okay, so we'll look at these aspects and we will do 1 more class on that. So please do not worry on that. Okay. All right. Now, coming back to this, what is the equation of the logistic? What is the equation of this curve right now? With respect to the line, the equation is y equal to mx plus c. With respect to the sigmoid curve, what is the equation? With respect to the sigmoid curve, what is the equation of this thing? Probability of repay is equal to what? Probability of repay is equal to 1 by 1 plus e to the power minus, e to the power minus, is it only salary? Is it only salary? No, salary plus c is a constant term. ठीक है, salary plus c होगा, ठीक है, same times salary plus c, intercept. All these things can be done in code. ठीक है, code we will see. We'll look at the code as well, right? Yeah. Last time we took California, right, guys? When we did the hands-on last time, what data set did we take? California, right? Just wanted to check with you guys. We took California, ठीक है? So classification I haven't done with you. That's an important thing. So logistic regularization मतलब ultimately classification है, ठीक है? So we need to understand classification in detail. There are so many aspects in classification, and I will ask you lots of questions today. Let's see how far you're able to answer that. ठीक है? So we'll see that. We'll see. So probability of repay is equal to 1 by 1 plus e to the power minus salary plus c. This is the sigmoid equation that we have got right now, straightforward. And now how so how is the concept similar with respect to this? So here, find out the optimum value of m and find out the optimum value of c such that we have a best fit curve. So find out the optimum value of m and the optimum value of c such that we have a best fit curve. The curve is basically best fit. That's what we are looking at right now. We've got a best fit curve that we are trying to learn right now. Okay. So in regression, you are trying to learn the best fit line. So the line can look like this. The line can look like this. The line can look like this. In logistic, you are trying to learn a best fit curve. So this is one important intuition to understand. Okay? Important thing to keep in mind as we are getting into the details of the code demos and the hands-on and other things. Okay? This is an important thing to keep in mind. Now, how do you solve this equation, guys? How do you do this? In linear regression, we were doing this using a technique referred to as right. We are talking about specifically we were looking at with linear regression. You're basically looking at it with respect to minimizing MSE, right? We were looking at with respect to MSE, right? MSE was basically how we are solving it. In logistic, what is the specific function that we are using? What is the specific function that we are using? Log loss, correct. Maximum likelihood estimation or log loss. Both are equivalent functions effectively. So we use the MLE technique to basically find out what is the ideal value of M and the ideal value of C such that the overall curve is best fit. Okay. So it will not be a complete best fit with respect to it will not be the complete best fit. There will be definitely some misclassification that will happen. There will be some green points misclassified incorrectly. There will be some red points that are misclassified. Generally, some misclassifications will happen. However, an important aspect to keep in mind is that generally, when we are building models like this, remember training data, you cannot achieve 100% accuracy. You cannot achieve 100% accuracy on your training data. So the accuracy is not going to be completely 100% on your training data. So training data, there will be some misclassifications that will also happen, generally speaking. Okay, yes. Why do we need to apply logistic when we can apply the sigmoid function over linear regression and find the output? I'm not sure about the difference. Well, well, Mandar, actually, that's a good question that you have asked generally, and I think oftentimes we don't. And very happy that you asked this question. In fact, we don't get to see many of these things generally in a scale-learned world because all that we do is dot fit, dot predict. But when you get to the details of the math is really beautiful. In fact, when you encounter deep learning, some of you who have read about a bit of neural networks and if you've studied about how deep learning is done, many of the times in deep learning, when you're doing linear regression and logistic regression, there is absolutely no difference, Mandar. In fact, there you do exactly the way you are specifying. You calculate some output and on top of that, you apply a sigmoid activation function. That's how you convert a linear model to a logistic model. So there is no difference. I would say internally, even the way you're solving it. By the way, this equation can be solved in two different ways. Okay, one is the maximum likelihood estimation technique. One is the MLE technique. So one way you can solve this is the MLE technique, right? That is one way to look at it. Maximum likelihood estimate, and the other way to solve it would be the logic regression. The two ways you can actually do it. So what is the logic? What is the regression way of solving it? What is the regression way of solving it? So can we convert this particular equation to a regression form? Yes, we can. What is the logic regression form, guys? Quickly, just to quickly summarize that. What is the logic regression form, which all of you have seen already? So log of, I would rather say ln. Ln is log of base e. So log of repay. So log of odds. Log of odds is equal to m times salary plus c. This is the logic regression form. So what is this equation? There are two primary equations to be kept in mind. One is the main sigmoid equation, the sigmoid curve or the S curve, right? This is the main sigmoid equation that we are talking about. This is the sigmoid curve or the S curve. And the next is basically with respect to the logic regression equation, and logic regression is the logic. This is basically why logistic is called logistic. Why is logistic regression called logistic regression? Because of this logic regression form. And this is very important because this is how you can basically start to even understand concepts like regularization. Regularization is not some rocket science concept in logistic. If you understand regularization in linear models like elastic net, ridge and lasso, the ideas are very similar with respect to logistic. Logistic, what happens? There is a parameter called capital C. there's a cost function that and we'll see that mathematically, theoretically. That's a very, very interesting topic. We'll see that. But that is what you basically tune there. The same way that you tune it for the alpha with respect to ridge and lasso, the idea is the same for logistic. And how can we do that? When we think of logistic like a linear model. Okay, because logistic regression is like a linear model. You can see it on your screen. Look at the square box that I put right now. Log of odds is equal to m times salary plus c. And just in case you want to understand a bit more in detail about this thing, how is it coming, and just in case you want to see that relationship, so what I'll do is I'll quickly bring it up for you. Okay, let me quickly bring it up for you. Yeah, and these parameters can be learned, guys. These specific parameters can be learned, exactly how it is happening, why it is happening. This can be specifically learned. I want to quickly show you specifically why and how this thing is happening. Let me quickly bring it up for you. So all of you look at the right side of your screen. Okay, it's a small derivation with respect to what we are talking about right now. I try to make it a bit smaller so that you're able to see both the aspects here. And this is a small relationship between odds and probability. I think most of you again might know this, but just for everybody in the audience, I'm trying to address it once again. Okay? Yeah, it's a relationship with respect to odds and probability. You can see right now. Okay, this is odds and probability. Take a look at the math, please. See if it makes sense, guys. Take a look at the math, please. So this is probability and this is odds. This is not some rocket science that we have done. Okay, this you might wonder, Sayan, we are all comfortable with what you did until here. We are all comfortable with what you did until here. Okay, but how did you get this? So the answer to that question is basically here. We have represented probability in terms of odds. So please look at this. This is the equation that you have learned, right? P of loan is equal to this. Now all that we have done is we have represented probability in terms of odds. That's it. I hope the basic math is absolutely fine with everybody. Take a look at this, all of you. Everybody's okay with this? What is the relationship between probability and odds? All of you are fine. If all of you are okay, I will move on. If one of you want me to quickly explain, I'll explain to you. Okay. But this equation we are all comfortable. Sigmoid we are all okay. But are you able to understand the relationship between this and this? Everybody's okay. Why we call it? How are we getting the logistic regression equation? This is fine. Everybody. Okay. Is it clear? There's one doubt somebody has. Was that explained? Okay. Okay. Quickly we will look at it. Okay. Quickly we'll look at it. Who's this? Okay. All right. We'll quickly look at this equation right now. So what we have here is, if you look at this side, all of you. Look at this one. Please focus on this part. Okay. Small demonstration of what we got and where we ended up. Okay. What is probability? What is probability of an event? Probability of an event is defined as number of favorable by total, right? Straightforward. That means, let's say India played 5 games and India won 4 out of 5 games. Straightforward. So there were 5 matches that India played and 4 out of 5 matches India won. Right now, 4 out of 5 matches India won, so the probability is 4 by 5. Now the question is, how do you represent this in terms of odds? What is odds of an event? Right? If India won 4 out of 5 matches, the odds of India winning are 4:1. So odds of an event is defined as favorable by unfavorable. How do you define odds of an event? Favorable by unfavorable. Okay, so 4:1. We often say odds of an event is 4:1. The odds of success is 4:1. Now, probability of an event, if you do the math right now, can be represented in terms of odds, and vice versa, odds of an event can be represented in terms of probability. It can be done. It can be mathematically proven. See, for example, if you can see what I've done right now, I'm saying odds is equal to P by 1 minus P. This is basically what we are saying. Okay, let me just express this algebraically. Let me just simplify this expression. What is P? P is F by T. That means favorable by total divided by 1 minus favorable by total equal to, if you solve this equation, what you end up getting? Favorable by unfavorable. That means odds is equal to favorable by unfavorable. So this is what we understand about odds. That means this equation is valid. So odds can be represented in terms of probability, and vice versa, probability can be represented in terms of odds. With this understanding, these are two thumb rule equations, but you don't memorize things in machine learning and data science, right? I mean, that's all for school days. I mean, you don't memorize stuff. There's always logic and there's always reason why something happens the way it happens. So now coming back to the equation that we saw, just to extend our conversation from there, coming back to the equation that we saw, you can look at this part right now. What I explained with respect to repay, I'm calling it a loan. Think of it like a loan repay. What is the probability you will repay the loan? So the probability you will repay the loan is given by 1 plus e to the power minus this. This is the probability of you repaying the loan. Now, what I've done here, I have represented probability in terms of odds. We already saw the equation sometime back. Okay, this particular part I'll share with you. I'll share this particular snippet with you so that you have some reference material. But most of you know this. And now what I'm doing is, I'm doing an algebraic simplification. I'm doing an algebraic simplification, and this is what I end up getting. Odds is equal to e to the power m times salary plus c. That's all we are doing. And finally, this is what you end up getting. You take log on both sides. These are properties of logs right now. What I've done right now from this step to this step, what I've done here is I've taken log of e on both sides. And what you're seeing here is a property of logarithms. Let me simplify this for all of you. It's the property of logarithms, guys. So if I take log of a thing, let's log of a to the power x, log of a to the power b, let's say to the base a, this will be equal to b. This is the property of logs basically, right? So it's like b comes this side, a cancels out, answer is b. So I've taken log of e both sides. That means I put a log of e here. So log to the base e. If I take log to the base e here, m times salary plus c comes this side, log e cancels out. That's how you end up getting the equation that we initially saw here. I think this makes sense, right? This is what we have derived here. This is what we get here. So these are two primary equations of logistic. To help us understand logistic, we primarily work with this equation. Log of odds is equal to m times salary plus c. Okay, hope this is fine with everybody. And this is the basic foundational idea behind logistic. Again, there's a lot of other theoretical constructs which most of you have seen. I'm not getting into those aspects right now. There is a lot of beautiful math around how this equation is derived. How this thing is actually coming, but that's a very, very different depth altogether, right? But I hope the basic intuition as to what is happening and how it's happening is clear to all of you. Now what we'll do is we'll actually get towards an exercise, right? Let's straight away come to an exercise, and what we'll do is we'll try to build whatever intuition we got with respect to logistic regression in this exercise. We'll try to build the same intuition with respect to some code. Okay, we'll do some hands-on coding like last time. We will go to Kaggle and we'll together work on a problem, and we will together build intuition on classification in general, right? Forget about logistic. The code is 2 lines, okay? It's nothing about code. Most of you are exposed to machine learning, and I think, so generally what happens is, again, mostly when we are learning a new topic, we always tend to be, thinking about theory and all that. But as I interact with so many candidates, and I've pretty much worked across most organizations, and, people know everything about theory, but when you ask them to implement something, they're like, okay, what is it? So let's do that. I think very early on, most of you are very early on in ML right now. I want to please inculcate this practice of hands-on. It's very, very important to get into it and get into the coding side of things. So given a choice, I would say given a choice, and again, not everybody is in the program for interviews. Interviews are one aspect of it, but if at all you're looking for it from that perspective, I would say given a choice, you are able to answer every single question correctly. What is a ridge regression, what is a lasso regression, what is elastic net regression. Although that's not part of what we're discussing, but some of you wanted to understand that. You are able to explain all of it about it, right? But the whole idea about it is, even despite knowing the theory, despite understanding what is L1 norm, L2 norm, regularization, and all those aspects, how does it impact your code? What is the application of it? Like from a coding side of things, how do you do? Now, let's see that. Let's understand that. Same thing in logistic as well. Like we know logistic, we know what is this probability and all these aspects that we are getting. But how does this apply to the code side of things? right? From a practical classification standpoint, how do we solve a practical problem and how do we apply these things? Let's see that. Let's see that. And then the same notebook, we will extend our conversation with respect to regularization. Okay. Yeah. So the data set I'll be taking, right now is a very interesting data set. This is PIMA diabetes. Before that, Purnima and Gaurav, Yuvraj, you guys got this part. This is fine. Does it make sense? You guys followed this? Explanation is okay. You are able to follow this part. Just to check with you guys. Yeah. Okay, great. Just remember these two equations right now, and I would say this is important because this same coefficients that you have, you have it in logistic regression also. So the same ideas that we have in linear regression, the same ideas are in logistic regression as well. So we'll see that. We'll see how it actually happens. So let's come back and let's look at PIMA diabetes. As a data set that we are looking at right now, I would encourage all of you to take some time and quickly just read the problem. And like last time, I would like you to create a new notebook and we'll be working on it together, okay? We discussed a round of missing value imputation last time, iterative imputer. We'll do the same imputation here as well. And we'll build a pipeline together on this, okay? With Logistic, look at the coefficients, do feature selection, understand the most important features, and probably in the next half an hour, 40 minutes, look at classification in a very different light, which you may not have seen so far, okay? That's the whole idea, okay? So all of you, take your time, 2-3 minutes, and let's understand this problem first, okay? All of you open up the Kaggle link and just explore the problem first quickly. All right, so guys, let's get going. I think most of you have read the problem, what is to be done, how it is to be done. So this is a very interesting data set. Anybody has come across this data set before? Have you come across this data set before? Quick check with all of you. No, just a quick check with the audience. It's a very popular data set, hence I'm asking. Anybody? Yes, Gaurav has gone through it. Good. Anybody else? No. Okay. Siddharth, you have gone through it. Good. So let me ask Siddharth and Rama, and let me check with Gaurav. Just a small interaction with you guys. What kind of accuracies did you get? And I know you are at a pretty advanced stage right now. Uh, in terms of whatever modules you have done, ensemble techniques and all you have seen. Just out of curiosity, how much of accuracy did you guys get? You got 90. What? Sorry, I. What's that? Gaurav, that's very hard to believe. 90 is very hard to believe, actually. You would have done something exceptionally good in that case. 84 is believable. 84 is believable. 84 is still on a higher side, yes. 90 is unbelievable. No, still, I think, did you do cross-validation, Gaurav? Did you apply cross-validation and then check? You did cross-validation, okay. That's interesting. Okay, but I think you probably are telling me training accuracy. It's very hard. I mean, it's hard to believe you're what is in testing accuracy. Okay, let's see. Okay, let's see. We'll see this here. New notebook, guys. Quickly, how do we simulate this thing just to get all of you up and running? We know this. Let's not waste time on this thing. We know this how to set it up. Click on new notebook, and we don't need GPUs for this. We can simply keep it as Python notebook. Click on create. That's it. Boom, up we go, and there goes our environment. Okay, all set. You can all parallelly do along with me. We'll code together. That's the whole expectation. We will do it together, right? We'll be applying all the aspects of our pipeline, and we build a logistic model from scratch. So I'm sorry. Oh, sorry. What did I? Give me a second. Just reverted to the checkpoint actually. Yeah. Now quickly give it a name. Logistic regression PMA diabetes. All right, so I'm just loading the current path right now, and this is my pandas read CSV, and this is what I'm getting. Okay, get ready. I'm going to asking lots of questions to you guys right now with respect to some very fundamental concepts. Not even talking about some very very advanced things that we've been discussing, but I'm talking about right from your EDA classes, statistics classes, some very fundamental questions. The way we have pretty much addressed the whole thing until now. Q is equal to outcome, and diag underscore kind equal to KDE. Okay. My question is, let us run for a second. Oh, sorry, SNS is not defined. I'm sorry. I need to quickly just import matplotlib. All right. So question is, how do you read this? How do you understand this pair plot? We understood pair plots. I understand pair plot, what it is. That's not my question. We know pair plots are what. That's not my question. My question is very specific. Understand my question. My question is very specific. How do you read pair plots with respect to classification? And logistic is just one subject that we're discussing. This is same as decision trees, KNN, SBM, whatever classification algorithm you take. My question is very focused, very specific. How do you read this pair plot with respect to classification? Question for all of you. I would like to hear from you a couple of insights that you're getting with respect to classification. How do you read this pair? I hope the code is fine with everybody. Just in case you want me to quickly ping this to you, this should be doable we're not discussing some rocket science here. We talked about this last class in California housing, so hopefully you should be able to read this. Yeah. Okay. Let me hear from all of you quickly. In your environment. I think that will be better, Mandar. Because I'm actually trying to show, the entire picture. Like I'm trying to show the whole thing, like just a quick visual pattern. Why don't you run the code once in your system? Let me wait for all of you for a minute. Why don't you all run the code and then we'll discuss it. Just take a minute, all of you, to quickly set it up and then discuss. Yes. Can you use the Python, Shubhendu? What are you trying? Are you using kernel this one Taggle only, or are you using something else? But it should be working fine. I'm not like Taggle itself. Okay. How are you doing it? Like, are you following the same instructions? Well, if it's something nitty gritty, then let's try to restart and check it up once, because yeah, this is something different you're saying. But are you just using the same path here? Uh, okay, so okay, once again, this is the same conversation we had last time, so I'm not sure if you have to go over it once again. Uh, so so Sridhar, were you there last time in our class? Were you able to simulate California housing? So if you don't see the data, that means click on add data. Okay, so what did we do last time? We clicked on add data, and you go to search by URL and you enter your path here. Okay, enter your path here, and that way you can get your data set here. You should be able to see something very similar to what I'm seeing right now, input, output, and you can see input by Indian diabetes coming. Your first, right, you have to run the, exactly, like you can see exactly what the path is, right? That's your path. Okay, so if you run the first line of code, you can see that path available. Yeah. Fine, Sridhar, just try it out once. Yeah. It works, okay. Okay. Tells us correlations. Correlation is very basic. That's fine. That's not what I was looking for. Correlation is basic. Yep. Yep. First block needs to be executed. Yes, that's true. Yep. That's how you, yep. So correlation is there. Correlation is definitely one thing that you get to see. But what else? Uh, there was a couple of correct answers I actually got. Hypothesis. Okay. Good. Can you show the clustering of 0 and 1? Can you show the clustering of Can show the clustering of 0 and 1 with respect to different variables, so right? Data distribution with respect to target. Good. I mean, data distribution with respect to target. That means what? From a classification perspective, I think most of you are, kind of beating around the same point. But I guess few of you have given the right answer here. Sachin has put it rightly. Colors will differentiate two classes. I think I got one good answer from Sachin, and the other person who has given something I was looking for is kind of Akash has given a beautiful answer. I was precisely looking for that. It gives you some kind of a feature importance, right? Beautiful, right? So I would say the diagonals tell you exactly which are important features. The diagonals give you a very good idea of the feature importance. The distributions, like other classes, very separate. And if you look at the diabetes use case, if you look at, all the classes are overlapping. They're completely overlapping classes we are looking at right now. So the use case that we are discussing right now is a very hard classification problem. That's why I was very surprised when Gaurav said he got 90%. So again, we'll have a conversation later on how that happened. But diabetes per se is a very hard classification problem. I think in your entire journey, you would have done iris dataset. Probably you would have also seen cancer dataset, Wisconsin breast cancer. There the accuracies would have touched 93, 94, 95, even up to 98. Those are simple problems. But diabetes, you are seeing that all the features, the classes are overlapping. So the whole idea of classification is what? How is classification fundamentally different from regression? What are we trying to do in classification? And because our conversation right now is with respect to logistics, what are we trying to achieve in logistic regression? What is the fundamental idea in logistic regression? Aside from the mathematics and all those things that we discussed, the fundamental idea of logistic regression is, let's say we have a distribution of classes right now. We've got red classes here, we've got green classes here. What we are trying to do is we're trying to learn a best fit line that best separates the classes. What is the line that best separates the classes? That is what we call the decision boundary. That's a term that we use called decision boundary. That's what you are trying to achieve in all classification problems. You are trying to find out a line that best separates the classes. You're trying to find out the line or the surface of best separation. In linear regression, you are trying to find out the line or surface of best fit. In logistic regression, you are trying to find out the line or surface of best separation. Now, if your data itself is like this, if you're visually unable to find any separation, and I'm talking about the diagonals primarily, correlations, features, and all those things we see, we understand that. What is correlation? That's not the point. The point is the diagonals, the pair plots tell you about how separated my classes are. And if you look at this data, very clearly you can see that the glucose column is a very important column. Because typically you can observe that the glucose, typically with respect to the glucose distribution, you can observe that the higher the glucose level, the more diabetic the person is, and the lower the glucose level, the less diabetic the person is. Red corresponds to diabetes, yes. Blue corresponds to diabetes, no. So the pair plots tell you a very good intuition they give you as to the separation, how separated these distributions are. Right? Yes. The curves, exactly. Shankar said, puts it very nicely. The curves are overlapping. If the curves or the distributions are overlapping, that means the variable will not help us. It will not help you to classify. Because what is classification trying to ultimately achieve? It is trying to ultimately it's trying to separate out your, it's trying to create that decision boundary. That's what classification is fundamentally trying to do. It is trying to create your decision boundary. If your features itself are garbage, then it will not help. So glucose is a good feature. Whereas if you look at blood pressure, it's a worthless feature. Blood pressure is a very bad feature. This is a very good intuitive understanding that you're getting right now. And I will prove it to you, with logistic regression coefficient, that we'll get the same thing. It will be useful only for binary classification, not really, sir. Even for multi-class classification, it will be helpful. What kind of statistical test will you use for that multi-class classification? You can use ANOVA test for that. Have you seen these kind of things, select K-based and all these things? Have you discussed select K-based? Have you heard of these things? In your sessions, have you talked about select K-based? Have you seen this? No? Okay. Clustering is a different aspect. Clustering is this feature selection basically. See, clustering is a different aspect. Clustering is I would say it's a slightly different aspect of it. Okay, we'll see that. I'll show you an example of that. In fact, this is how hypothesis testing beautifully marries into machine learning. Hypothesis testing otherwise is a very theoretical topic, but how do you practically use statistical testing? One thing that we can do is, yes, I think as Shubhantu rightly says, age is also little less overlapping, correct? Even the age feature is slightly less overlapping. Even the age feature, you will find some separation. That means people who are slightly older are slightly more prone to diabetes, correct? And people who are slightly less older are less prone to diabetes, correct? And even the body mass index feature, if you look at it, the body mass index feature is also pretty good. If the body mass index is high, you're more prone to diabetes. Generally, I think obesity and diabetes are correlated to some extent, right? If your BMI is high, then you're more diabetic. And if your body mass index is low, then you're less diabetic. But if you look at it, these are worthless features. The diabetes pedigree function, very bad feature. Okay. And for that matter, blood pressure, very bad feature. If your blood pressure is high, you may be diabetic, may not be diabetic. If your blood pressure is low, you may be diabetic, may not be diabetic. Equal probability. So blood pressure can be high due to any reason. It doesn't necessarily mean, yes. Not interesting. I would say skin thickness is also, is very poor correlation, son. It's very poor correlation. It doesn't really tell you anything about it. So bottom line is it's a very bad data set. We have taken a very, very hard problem to model. We've taken a very hard problem to model. And what we are seeing right now with respect to this data, what's that? Hold on. Okay, give me a second, guys. going to reload my kernel 1 second. Okay. Yeah, and the other thing I wanted to quickly show you is, I think most of you have seen random forest and all these things, right? I can straight away show you one. I won't get into that topic right now in detail. It's a bimodal data set, correct? I think you were referring with respect to that. It's very good, yes. And it is bimodal for a reason, Sans, and I will talk about that for a second. But if you do your sklearn ensemble and use any of the tree-based models here, use any of the tree-based models right now. Let's say if you use any of the tree-based models right now, just do a random fit on your whole data. So what is my X? I think I'll just quickly separate this out. So outcome is basically my X variable. So just quickly separate this out. So what I'm trying to convey is that even the feature relationships will interestingly convey this whole thing to you. So demo.drop, and you can drop your outcome variable with access equal to 1, and y is equal to demo of the outcome variable, right? Outcome variable. I'm sorry. Okay, straightforward. And here straight away gb.fit x comma y and gb.feature importances. Right? We can look at feature importances. Now, if you do this, if you run this piece of code, I'm sorry. If you run this piece of code, you'll straight away see the warnings are a bit of a trouble actually. I'll just quickly go back and ignore the warnings. And the answers that you see right now are very much in line with what we got some time back. So very much the inference that we got some time back. Ignore the warnings, please. Okay, that's what we're getting right now. Look at this, all of you. Look at this. Look at this, everybody. The second feature. What is the second feature? The second feature is basically plasma glucose level. Okay, I'm just going to quickly ping this code to all of you. Okay, x fit comma y, and this is the thing. You can all please parallelly code along with me. That's the whole idea. Okay, so we learn together. We do it together. Okay. So you can see right now the second feature has the strongest correlation. Gradient boosting feature importance is one of the most robust ways to evaluate the quality of a feature. And what I'm trying to convey to you right now is the pair plot relationship we saw visually, and the thing that we are able to mathematically get with respect to entropy information gain logic is pretty much falling in sync. That this also tells me that, hey, you know what, the outcome, the glucose is a very good feature to predict diabetes. The feature importance is 40%, and body mass index is the next most important feature. And I think, as you rightly said, age is the third most important feature. We are clearly seeing that the top three most important features. The rest of the features are not so important. We can talk. So these are the three most important features we're spotting straight away with respect to feature importance. Right? This is what clubs as a feature selection technique. Iteration 1, we're looking at a little bit of feature selection. Okay, feature selection. Now, what other ways can I do feature selection? I will quickly write a piece of code. So what I'll do is I'll quickly write a piece of code right now. And I'll let you ponder over it for a second. Okay. Again, don't worry what the code is. I'll quickly write a piece of code and let you ponder over it for a second. Can you repeat? Yeah. So, Sans, you have seen feature importance. First of all, feature importance you have seen, right? You understand the basic idea of feature importance. Just wanted to understand. Great. So you understand. Good. So feature importance, it applies for every tree-based model, whether it is decision tree, random forest, bagging, boosting, every tree-based model. Okay, so so people who have not seen, don't worry. Please don't worry right now. I mean, the feature importance is a different thing. It's basically a property of decision tree, effectively, right? Decision tree. Yes. What's that? Yeah. What all other techniques? Right. So RFE. Yeah. Hold on. 1 minute. Hold on, sir. Please hold on. Look, let me explain that. Okay. Let me explain that. So, Sans, first of all, for you, feature importance is a decision tree based technique, right? Lasso is a very basic technique. It's not practical. I know Lasso is generally talked about in theoretically its use for feature selection. Not practical. There are more robust techniques that are used for feature selection, which is what we are doing right now. So one of the most robust techniques for feature selection that we use in industry is feature importance. It's a model-based technique. Second is RFE, and I would say another better good technique is your select K-based feature selection based techniques. Okay. So the entire repository of what I'm discussing right now It's part of there's an entire module on feature selection in sklearn. There's a library available for that. Okay, your lasso doesn't find a mention here. Lasso is not regarded as it can be used for feature selection, but it's not practical. We don't use it generally. Okay, so this is the entire repository of feature selection. So we use select k-base, statistical techniques, statistical tests, hypothesis tests, t-test, ANOVA, chi-square. Okay, these are the statistical tests that we use. Then you come to model-based techniques like recursive feature elimination. This is what you talked about. RFE is a good technique. What you've learned is a good technique. And then you also have something called select from model. Select from model is basically where we look at generally things like feature importances. Feature importance is what we are looking at right now. Okay, and this is the pipeline way of incorporating the whole thing. Okay, yeah. So the reason, Rajat, I'm saying it is fundamentally based on a linear model. Lasso regression is fundamentally based on a linear model, right? Because it is fundamentally based on a linear model, practically data is non-linear. But Lasso is ultimately fitting a linear model, no? So whether you talk about Lasso, you talk about Rage, ultimately they're fitting linear models. They're based on linear models. If my data itself is non-linear, in a multi-dimensional space, if my data itself is non-linear, the relevance of those linear models are limited. I would say in simple problems, they work out fine. But in more practical problems that you will encounter in industry today, in today's day and age. See, regression, guys, is a technique that has been there for centuries. The term regression was first coined in 1800s. So all these topics, linear regression and logistic regression particularly, these techniques have been there for centuries. It's not a new topic at all. So we've been doing this for a long, long time. Some of the more advancements in machine learning has come due to ensemble techniques, gradient boosting, random forest, the topic that you're seeing right now. Okay, which is why I would say linear models are a very nice way of approaching, data science problems practically. So one of the reasons why they are preferred, then you might ask me, Sayan, why is it preferred? Why are we doing logistic regression? The reason why logistic regression is preferred, the reason why linear regression is preferred is basically to understand your model for interpretability purposes, right? That is the primary reason. Remember, regression as a technique is not only used to do prediction. There's a fundamental difference in thought. We often think that we build a model only to predict. Not really. We don't build a model only to predict. Historically, statisticians have built models to understand the nature of the relationships of data. So let's say we have got an X and we have got a Y. Okay, let's say the patterns are like this. Then what statisticians used to do, and regression is actually a core statistical topic. We club it as part of machine learning, but it's a core statistical topic that has been done for centuries. Statisticians have historically used a regression technique, whether it is linear, whether it's logistic. They have used that technique to study the relationship of variables. This is a primarily descriptive statistics technique. What is descriptive analytics, guys? Descriptive basically means looking at data and figuring out what happened, why it happened. Descriptive diagnostic. You're trying to understand the relationship of your features with your output. You are not trying to predict anything. You are just trying to understand, hey, you know what? It's more like establishing causation. I think you've heard about this countless number of times, but nobody quite gets to that. It's like, if I really want to understand causation, that's where regression models, linear regression models really find a use case. You want to find the cause-effect relationship. You want to understand, okay, this part of X causes this part of Y. That's where really regression still has relevance. Now, when you extend this conversation to a prediction standpoint, can linear models, whether it's regression, linear or logistic, can they be used from a predictive standpoint? Yes, they can be, but practically in the modern era, they have no relevance today. Because if I'm solely concerned about prediction, I've got much more powerful algorithms available today. Linear, logistic don't even have a use case in that domain. Linear regression, logistic has a lot of use case with respect to understanding relationships in data, but they have no use case in, as I said, making predictions. And feature selection fundamentally is all about looking at the non-linearity of your features and seeing how they impact your output. So if your data is so complex, then I would say we will not use linear models to evaluate features generally. That's the whole idea behind it, yes. No, I'm not saying that. Industry standard tree-based models are industry standard today. And even decision trees are not new exactly. It's not as old as regression. Regressions have been there for, as I said, that it's been there for a long time, but decision trees have also been there for decades. Almost all bank finance-based models, credit loan, prediction models, they're based on decision trees, tree-based models. Tree-based models are a standard practice in industry today. In traditional machine learning, I would say. Okay, so tree-based models are used in a big way. Mostly ensembles you will find, yeah, generally. Okay, anyways, let's come to that. Let's come back. This is again very different. let's come back. So, Sam, there was a question. Sorry, I think to answer your question, I deviated a little bit. So the question basically was, what is feature importance? Feature importance internally does entropy information gain computation, and it basically evaluates what is the what is the overall net importance of that particular feature. That means if you use the glucose feature, just to help you understand it a little bit better, that means if you plot let's say all the decision trees in gradient boosting, most of the times on your glucose feature will come in the root node. You can relate to it. If a feature comes in the root node, that feature is more important, right? So 9 out of 10 times, think of it that way. It's like saying 4 out of 10 times the glucose feature net will come in the root node. Think of it that way. That's the intuition behind why it's an important feature, because it reduces entropy in the maximal possible manner. Okay. I can quickly plug in a little bit of feature selection, other techniques. One more technique I'll quickly talk about. This is with respect to select k-best. And here I will try to marry your hypothesis testing concept with respect to classification. Classification is a very deep topic. It is not just fit predict. And that's what I'm trying to get at. So let's see that. Let's see this. sklearn dot feature selection, sklearn dot feature selection, import select k-best. Okay, you can just observe what I'm doing right now, then we'll do it together. Okay, then I'll give you some time to code it out and understand the outputs. And this time I'll ask lots of questions, because hypothesis testing is something all of you studied. Okay, I would like to hear from you what the outputs actually kind of convey. Okay, so here I will also use a F classification. F classification is ANOVA test. I'm straight away doing ANOVA test right now. How can we apply if you are both categorical? Siddharth, you will do it separately. If so, just to clarify, Siddharth, if you're using feature importance, gradient boosting will automatically handle. If you're using univariate statistical techniques, you have to do it separately. Chi-square for categorical and ANOVA for numerical. Okay. Okay. So I'm going to quickly go back and fit the model. Select k-best. I'm going to quickly put in a select k-best here. Select k-best, and here I'll just use the respective algorithm. F classification, and I can just put a number of 3. That's basically how many features I want to choose. Let's say I want to choose all 8 features. I want to select all 8 features. And finally, skb.fit. The code is very simple, as you can see. Specifically, fit transform. Why fit transform? It's a pre-processing technique. Feature selection is the kind of pre-processing that we are trying to do here. And that's what you get. We are not interested in this output as such, but what I'm interested to see here is basically the p-values. Straight away, I'll look at the p-values, and now my question is to all of you. I'll ping this code to everybody. Run this code. How to define number of features? Sir, this is the way we do it actually. This is the positional argument that you put. I'm not actually doing feature selection. I'm using all the features. We're getting towards that. Hold on, we're getting towards that. First of all, my question is, what do these p-values actually mean? You run the code in the system. You tell me what does the p-values mean right now. Let's quickly see. Start from there. How do you interpret p-value? How do you marry your hypothesis testing p-value that you studied back that time? And how do you marry that conversation with respect to what we are doing right now, with respect to a classification problem and that to a diabetes data set? Let me give all of you 2 minutes time to maybe recap some of those things and give an answer. Take 2 minutes here. Okay, I'm just going through most of the answers, and I think most of you are able to recap the things quite well. Good. Riches and the hypothesis, I think. So what I'd also do, maybe give a little bit more time to you guys, and parallelly also do the manual way of doing it. Not sure if you've seen these kind of things, but just to kind of show you the other way to do it as well. So you can just follow along with me. That's fine. Scipy.stats as stats, and this is the stats library that we're using right now. And this is the manual way to do it. We don't have to do it like this, okay? Normal way to do it would be you have to manually define t-test, okay? T-test, IND, t-test, all that you have to manually do, right? So this is the manual way to do it. And now straight away I can use t-test, IND. Okay, t-test, IND I can do with respect to diabetes and not diabetes features. Does F regression use ANOVA in the backend? Rama, yes, it does. F regression uses ANOVA. Exactly, it uses ANOVA in the backend. Even classification is using ANOVA, by the way. This is ANOVA is basically what relationship between categorical numerical variables. Okay, yeah. Okay, I'm going to write a little bit of quick piece of code. I'm going to write here. Just looking at some of the questions that you guys have asked. ANOVA checks the variance between, yeah, that's the theory behind ANOVA, correct? Yes. No, VIS is for a different purpose, Gaurav. VIS is for multicollinearity. VIS is basically used for correlation between features, correct? Yes. Exactly. I think pretty much most of you are able to get it. I'm just reading the comments so that I'm just able to understand whether all of you have understood correctly. I think most of you are right on the right track. P values detect the significance of the features, correct? If the P value is small, that means the feature is more significant. In this case, if the P value is very, very small, so you can see the glucose P value is very, very small. That means the feature is very, very significant. Exactly. Yes. Good. So I think the separation is very meaningful for glucose, correct? And we are able to evaluate that. And now we've done two types of tests. Oftentimes people ask this question: Science, should I go for this? Science, should I go for this? Which technique should I use? Should I use feature importance? Should I use the statistical univariate test? What technique should I use specifically? What technique should I use to evaluate this? So what this tells you is, no matter what technique you use, if a feature is a good feature, now you also learned RFE, right? So what technique should you practically use? So the bottom line here is that if a feature is a good feature, no matter what technique you use, you will always get good performance. You will always get the same answers actually. If glucose is a good quality feature, whether you use feature importance or you use the p-value technique, in both the cases, you will get good performance. Basically the same answers. And Ashok, you can try with RFE technique also. Even RFE will tell you that glucose is the most important feature. That's the crux of it. Because there are multiple feature selection techniques, right? It's a very common question people ask. We have learned feature importance, we have learned this, we have learned that. All are valid techniques. Your initial topic was statistics. Statistical techniques are the first things to be applied. Okay, even the feature selection documentation says that univariate statistical tests. That's what you're doing. That's the crux of it. Now, which technique is better? There's no better technique. But the point is, if your feature is truly a good feature, all the techniques will give you coinciding results. Okay. All right. Anyways, let's do it in a manual way. Just one. You don't have to worry about this one, but just in case you're curious how it's coming. One of you asked me what is t-test IND. It's very important. It's a statistical t-test. It's a manual way we conduct a t-test. So plasma diabetic. I'll quickly just write a quick piece of code for this. So this is double equal to 1. So when the it basically means when the class is double equal to 1, please extract the plasma column out of this. Please extract the outcome glucose column out of it. Okay, that's basically my code I'm writing. Don't worry, guys. Let me just complete this. I'll explain to you what I'm doing here. And this is plasma of non-diabetic. Okay, it's plasma of non-diabetic. And if the outcome is equal to 0, that means extract all the non-diabetic patients and extract their glucose levels. And what I will do here, I'll go back and enter an array of, just give the two numpy arrays as argument. That means plasma of diabetic, comma, plasma of non-diabetic, straightforward. Okay, just put it in, plug it in. T-test is not defined. Okay, what happened here? I'm sorry, stats.t-test ind, sorry. Yeah. Okay, look at this. What I wanted to convey here, and I'll do one more piece of code here for you. This will be with respect to blood pressure. So what I wanted to convey to all of you here was, whatever I did here manually, the same thing SK select K basis doing automatically. So this t-test is nothing but this t-test, whatever code I used here right now, I'll just quickly ping the code to all of you. Whatever code I used here right now, this code is basically used to manually do t-testing. Whatever t-test you have studied in your statistics, this is the way you practically use t-test from a, I would say from a machine learning standpoint. This is the way you practically apply t-test from a machine learning standpoint. So you do t-test, find out the p-value of the feature, and once again, what it tells you, first of all, the answers are exactly the same. You can observe that, 8.93 into 10 power minus 43, 8.93 into 10 power minus 43. Answers will be the same. Okay. Statistic is t statistic, Shubhendu. What is this statistic? T statistic. T statistic is you remember that? T statistic x minus, difference between the mean by standard error. Okay? Yeah, that's a t statistic. Now, what is the intuition behind this thing that we are seeing? Okay, just finally summarize the whole thing and let's move on. So glucose in the x-axis, okay? Glucose is the x-axis, and if the glucose level is low, person is more prone to diabetes. If the glucose level is high, person is more prone to diabetes. If the glucose level is low, person is less prone to diabetes. If the glucose level is high, person is more prone to diabetes. That's what we are seeing right now. So turns out the separation is very meaningful. Okay, let me just draw this out manually for you, just for everybody. Wanted to just quickly show it to you once again. This is, let's say, mu of non-diabetes, and this is, let's say, mu of diabetes. Okay, so mu of diabetes. Actually, standard sample mean. Okay, what is the I should actually read this as sample mean. That's okay. Null hypothesis, alternate hypothesis. What is null hypothesis? Null hypothesis is basically mu of nd is equal to mu of d. An alternate hypothesis is what? Mu of nd is not equal to mu of d. So what can you conclude from t-test? I'm just answering that question. Because the p-value was small, what did we learn as part of our t-testing? If p is less than 5%, what do? You reject null, right? Reject null, else you fail to reject null. That's one of the important crux of what we have learned as part of t-test. No, all of statistics, that's the fundamental thing that we have learned. If p-value is less than 5%, reject null. Right? So you can see right now, p-value is very, very small right now. 10 to the power minus 43, right, Shivangi? So you will go back and you will reject null. If you reject null, you will accept alternate. Accept alternate basically means what in English? What does it mean in English? It means that there is a significant difference between the distributions. The glucose level of diabetes patients and the glucose level of non-diabetic patients are significantly different. There's a strong separation I see. That's the way to interpret it. There's a very strong separation between diabetes and non-diabetes. Right? I hope this makes sense. So this is pretty much the crux of what we have achieved, and pretty much what you have said, what you have answered, most of you is absolutely correct. So smaller the p-value, the more significant the feature. So don't worry about this. This is a very manual way of looking at the whole thing. Something you must know, because that's the crux of t-test, statistical t-test that you have studied, hypothesis testing. But when you go to more advanced modules, like we are in machine learning right now, we don't have to worry about that, because practically we are looking at better ways to do it, like select k-base. It automatically gives us the same answers. Right with the large decimal place, the same values, 8.9354, same p-values. Okay. Hey, what is the t statistic? T statistic is your that's pretty much the z score. T statistic and z is just like z statistic. Make sense? No, Rama. There is no concept of threshold in machine learning. All that is theory. Practically in ML conversations, there's no threshold conversation here. So what we practically do in feature selection is we say that, okay, I'll tell you, Rama, if you look at the data right now, I'll tell you, look at this, look at this, Rama, 3.8, no, the p-value is actually less than 5%. So we will say this is a good feature, it's not a good feature. So p-value is always comparative. Machine learning is always a comparative conversation we have. It's not like a fixed conversation like, okay, 5% p-value, no. These are all p-values we are getting for all the features. Now, out of all the p-values, we say which p-values are the lowest. The p-value of glucose is the lowest. That means glucose is the most important feature. That's the way to look at it. So p-value of glucose is the lowest. That means glucose is the most important feature. Okay, is it clear? Yeah. Okay, great. So let's. Why we confined to 5? No, we are not confined to 5%. Nobody is confined to 5%. That is only the topic that was raised. That's why I answered. We're not. There's no 5%. Okay, forget about 5%. It's just p-value that we're getting. Now, Madhira, what we do is we basically go back and we compare with respect to all the p-values. The smaller the p-value, the better it is. Okay, the smaller the p-value, the better it is. Right. All right. Now let's carry forward the conversation. And now what I would like all of you to do is, please tell me if there are any missing values in my data. Think very carefully before you answer. Okay. Think very carefully before you answer. Think very carefully before you answer. No. See, Gagan, that's again a very, that's a very statistical way of looking at it. To understand one thing very carefully, hypothesis testing, one way to look at hypothesis testing is from a very theoretical statistical standpoint. The other way to look at statistical testing, the hypothesis testing part, which we are doing right now, is to use hypothesis testing from a machine learning construct. That's important. That's what we are in this thing for, right? The hypothesis testing from a core statistical standpoint is different. There you are doing an experiment, you collect sample data and you do X, Y, Z, all the stuff. Right now we are having a very different conversation. This is basically using statistical tests for machine learning. In that conversation, just looking at that 5% has no significance, right? You have to do a comparative analysis with all the people. That's what I was meaning to say. Okay. Are there any missing values? No, if the answer was no, I would not have asked you. Okay. So if the answer was no, I would not have asked you guys. There are definitely missing values. No, might be is a very diplomatic answer. Zero values are there, exactly. And some of you in the initial part, you told me about clusters. That's exactly why the clusters are coming. There's zero values, right? There are missing values. Absolutely. You please do a describe method, guys. Do a describe method. Do a demo.describe, and you will clearly find those missing values. You'll clearly find the missing values right now. Let's do this right now. Do the describe method. You will clearly find missing values right now. So missing value doesn't just mean like California housing we saw that time. That was one use case we studied, right? Where the data itself was missing. But practical missing data, most of the time in real world, can be like this. Don't just look at a demo.info and say, okay, no missing values. No, practically explore your data. That's what we say EDA is important. There are zeros in the columns and it doesn't make any sense. How can a person's blood pressure and insulin level and all that be zero? It's not possible. This is where we will do imputation today, right? Iteration 1, we will build a basic model. Iteration 2, we will do imputation and see if the model performance actually goes up. Okay, we'll do that. And then let's us go back and apply a pipeline of techniques and see if the model actually improves. Okay. So there is definitely some missing values that are out there. Aside from that, remember logistic regression also makes fundamental assumptions about the distribution of your data. So logistic also makes fundamental assumptions about your distribution. So logistic also assumes that your data should be normally distributed, all those things, right? So right now my data is not normally distributed. You can clearly see that right now. If you look at my data, it is not symmetric. It's not normal. So logistic also has these assumptions that it makes, right? So you have to make your data more symmetric. So that has to be done. So power transformer, imputation, and logistic. So can I ask all of you to do one quick thing? Just one quick thing. So apply power transformer. Apply power transformer. And build a fundamental iteration 1 logistic regression model. And while you're doing this, and what is most important here is to learn the comparative analysis. Actually, the comparative analysis is very important. So while you're doing this, I would like you to also compare your performance with respect to what you're getting here, and after you do the imputation, what you get there, which we'll also see right now. I think, guys, we talked about pipelines last class, right? Just wanted to quickly check with you. We talked about pipelines, right? Pipelines introduction. We talked about pipelines. Great. So I think our work is We don't have to do it manually. I mean, put a pipeline. But I need to give you one small hint here. Uh, I think we don't have to do it manually. These are the initial exploratory techniques we are doing to understand. But hey, I mean, we have seen pipelines. Okay, we're gonna put all of it together right now. Okay, so RFE, everything, just gonna push it in a pipeline, and that's it. So the workflow becomes so simple now. Uh, One thing I would like you to do as we move on with the conversation, I would like all of you to take a random set of 20. Okay, this is the initial train test bit I would like you to do, just so that we are on the same page and we are having the same conversation. Okay, just so that when you build the model, you and I, we should see the same answers. Okay, just do a power transformer and then run the model. Let's see what you're getting. It's 2 minutes. I'll give all of you. Use the same pipeline code from last time, California housing. Make the edits. See how easy it is to change it. Make the edits. Push it in. sklearn remains the same, whether it is classification, whether it's regression. Doesn't matter. The same pipeline, the same concepts, the same methods will work the same way. There's no difference. Okay. Relevant code. No. Right. I will ping. But whole idea is, you were there last time. Hello, or you missed the session or something? Okay. I'll ping it. Just waiting for people to do it. Then I'll ping. Yes. Okay. No problem. I'll ping the code. Yeah. Generally, Rama, that's a slightly advanced conversation, but there are a few other techniques also. We use clustering techniques as well. I think clustering as a module you have not seen yet, I guess. Unsupervised learning, dimension reduction. There are a few other advanced ways we do it, but I think that's for a later time we can talk about it. Right? But clustering as a whole is one very popular way we identify anomalies. You would have heard of one field of study called anomaly detection, right? We use clustering techniques for that. Credit card fraud. How do we detect outlier transactions? So clustering is a great way of doing that actually. Yeah. But that's for a later date. But just to give you some guidance on that, yes. Okay, I'm going to quickly just do it along with you guys. So from sklearn model selection, import train test split, and import sklearn linear model, import logistic regression. So to get done with a few of these things, sklearn pre-processing. So to push it all out in a pipeline and just get this thing done. California was a little simple last time. So I'm going to put in 3 more pre-processing steps here. And I'm going to put an iterative also here. That will make it more interesting. So I'm sorry, iterative will be a different. Okay, let me just first of all do with power transformer, then I'll put an iterative. Okay. What else? We're gonna do a train test split and push it into a pipeline. That's all that we'll put in here. Okay. That's my train test split. I've taken 20, and then the pipeline, straightforward. Okay. In the pipeline, I'll put in a power transformer and a logistic regression. Okay, that's the way I'll create a pipeline. I'll just copy this code to all of you. I'll just quickly copy this code to all of you right now. So here, I'll do power transformer and logistic regression. Okay. Now, so as you can see, the performance will not be great. How do I get intelligence? Hey, that's tab, Sandeep. That's tab. So you write a piece of code and you hit tab. Okay, tab. Press tab, please. Okay. Hit tab, you can get it there. Okay. That's my train test script. Most of you have done this part, you know. And there it goes. There goes the pipeline. There goes the pipeline. There goes the pipe.fit. May I power transformer? We had this conversation last time. I think power transformer is basically used to transform your data, make it more Gaussian. Okay. Please look at the session we had on California housing, but the quick short answer is it helps to make my distributions more Gaussian. Okay. Yeah. Okay. No, capping is not the right thing. Capping is a very basic technique actually. See, how to use clustering, Rama, is that's the conversation. Maybe let's for another day. Yeah, that's what clustering is a different topic. Let's talk about that later. But you can use clustering techniques. You can look at inertia, silhouette coefficients, and you can see that whether a particular point is very far away or a particular cluster is very distinct from another cluster. That means that it could be an outlier. It's a multivariate outlier detection technique. Okay? So that's a different conversation. Yeah. But capping is not clustering. Capping is, you don't need clustering to do capping. Sorry, I mean to say you don't need to do capping to do clustering. Or the other way around, I'm sorry. You don't need to do clustering to do capping. Yeah, plus capping is, is a basic technique. Capping is not even a technique what's talking about. That's very basic actually. Yeah. Okay. And capping is oftentimes a very incorrect technique. I'll tell you why. Because if a person is making a lot of money and you say, okay, no, I want that person to be capped within this much. No, you're fundamentally misrepresenting your data. If you say one value is very high in the box and whisker plot, that particular value is above your upper whisker, and you're simply capping that value to upper whisker or quartile 3, you're fundamentally, tampering with how much money that person is actually making. So that is I would say a highly questionable technique. Okay. Okay. Now, everybody is getting 74, 78. All of you are with me until now. Everybody. We are all on the same page. Okay. Error. Debugging errors are the hardest part right now. How do I debug it? You want to run it once again? Maybe this one part you missed out. Probably check it out once on. Okay. Unknown label continuous. Sans, what has happened is you have copied the linear regression code. Most likely you're using that right now. 100%. That is a very common mistake. You would have taken the code from linear regression, right? You would have probably not missed changing the code. Check it out. I think you're using linear regression right now. Yeah, so probably that's a check. Yeah. Yeah, because continuous label actually, yeah. Check it out. Only the data set you have taken is different. Yeah. Yes, Sachin. Just go through that once. Yeah, we did talk about the powers and all those things. Yes. Okay. Next thing that we look at right now is we will look at the the imputation part. This is slightly different because last time in California we straight away did an imputation. Right now what we'll do is something a bit more interesting. So right now I cannot straight away do imputation. Remember, because my demo column says that my features are missing, right? My demo column says my features are present, so I cannot straight away come back and do an imputation. So to do an imputation, what I have to do is I have to first put a piece of code here, and I have to say that, hey, wherever the plasma column, I'm only just taking plasma right now. There's no particular reason, but I'm just taking plasma and showing you. So I'm saying whenever the value is equal to 0, 0 is a valid value, okay? Whenever the value is equal to 0, you are explicitly telling Python that, hey, Python, please replace that 0 value with NaN. That's it. That's all we are saying right now. So whenever the value is equal to 0, please replace that value with equal to NaN. So we are doing this with respect to plasma and pressure columns. You can say do this with respect to plasma. Plasma means glucose actually. And this is pressure as in blood pressure column. Okay? So we're doing this with respect to these two columns right now. So plasma and blood pressure column. And once again, the same code, I'll just copy paste here. So you're explicitly instructing Python that, hey, Python, you know what, these columns cannot be zero. So whenever you see zero, you better interpret this as nulls. And you can do for the others also. Just a simple demonstration I'm showing you. And once you do that, you will observe in your demo.info, that now the true state actually gets reflected. Now glucose, you are seeing that yes, there are 5 missing values, and blood pressure, you are seeing there are 733 missing values. You will observe this, the true state actually being reflected here. Okay, that is one of the things you will observe. So after I've changed my data here, rest and all is good to go. So what we can do is we can basically execute the same code itself. I can just copy paste the same code here. Only this time I will put an additional piece of code. I'll put an additional piece of code for iterative imputer. Okay, iterative imputer, I have to put in something else. What I have to put here? Only with respect to iterative, I have to put this part, experimental. Okay, this library I have to basically put in. And the other thing will be impute this with missing value, because if you don't do the imputation, what will happen? The code will give you incorrect answers. The model will not work. So first do the imputation, then transformation, then logistic regression. Run the code, and this is what you will end up getting. Okay. So first imputation, then transformation, then logistic regression. Okay. This is the way we are actually going to do it. Right. I'm going to quickly go back and run the cells once again quickly. I'll ping this to all of you right now. Yeah. It is. We are using a pipeline right now. I'm using a pipeline right now. Yes. Wouldn't these zeros be replaced? No. Power transform is used for a different thing. Power transform is to make my distributions more Gaussian. Power transform is to use is to make my distributions more Gaussian. Imputation, iterative imputer is for a different reason. Power transformer is used for a different reason. They are both used for different reasons. They are not the same thing actually. Imputation is used for imputation techniques. It's an imputation strategy that I'm using. Right? Makes sense? Power transformation is used for a different reason. So the use case is different here. Okay? Yeah. You can also add in a scaling step here. There's a scaling step you can also add in here. Iterative power transformer, and the same way that you generally add a scaling step, you can put in a scaling step also here. So just after power transformation, you want to additionally scale the values. The scaling you can also add in if you want. Okay. It's an additional pre-processing step I'm putting in here. Yes, Sant. I'll be going and executing just sharing the whole thing with you in a second. Okay. I'll be doing that. Yes. Now the question is, remember, scaling will not create a big impact. What is the reason behind this? Scaling will not create a big impact in the whole performance of your model. And what is the reason why scaling will not create a big impact is because, this is the reason is because, so why will not scaling create a big impact? Because power transformation is anyways doing scaling, I would say. Power transformation is anyways doing scaling, right? N estimators is basically, the default is taken. You can try it out. You can use linear regression also here. Okay. Basically, normal regression model is taken. Okay. Regression model. And if you check the code right now, the demo data frame, how it's happening and the way it's working out, you can check your data frame right now. You can check your data frame. Demo.head, you can see right now that demo.info, you can check it out right now. You can actually see, you can actually see that my data has missing values right now. Okay, these are the missing values that we have. And after I did the imputation, I'm looking at some ways to handle that data. Okay. You can try out a different technique. You can absolutely try out a different technique, and you can probably, you can try out a different technique to handle that imputation better. You can do that. Okay. Let me quickly ping the code to all of you. the way you can actually incorporate this thing. Scaling is not mandatory in this whole thing. Scaling is not absolutely mandatory. It's not required. Okay, you can opt to do it. You can opt not to do it. Completely up to you. Not required. That's what I say. Scaling is not required right now. You can absolutely remove scaling. Not required. I just wanted to manually show you that scaling can be done. You can incorporate multiple pre-processing steps, but scaling is not required here. Absolutely not. Okay. Yep. And if you want to do it in a slightly more robust way, you can probably keep all the features under imputation based on that. Yeah. Exactly. That's the same process will work here also, Rama. Correct. The same process will work here also. Absolutely. Once you're absolutely sure the imputation is working right, then you go and plug it in. My assumption is that until now we've already done that. So ideally that part remains the same. So basically, you know what, Rama, before I put the final pipeline, the pipeline is the final model building step. Everything you push it here, right? But before you do this particular part, what I will do, Rama, is I will add a code cell before that. I will do exactly what we did in California. I will analyze that is the imputation impacting my distributions or not. If they are not, then I will basically use the same logic and do the final imputation. Okay, makes sense? Yeah. Can we do imputation for all the features? Yes, you can. Yes, you can. Absolutely. So if there are multiple features, the multiple missing values here, right? All the missing values are eventually getting addressed. See, here I showed you only with respect to glucose and blood pressure. You can try it out for the rest also. You can try it for skin thickness, insulin. Let's just see right now. Skin thickness, we have a 0 value coming here in skin thickness, and insulin also 0. Body mass index also 0. You can add in these features also. You can do that. So for example, all of it will be handled together. Okay. Here I just showed an example with respect to 2 features, but you can add in all the features. Insulin I can add in here right now. I can add body mass index here. Body mass index is BMI. And here I can go back and add skin thickness. So I'm doing imputation for all the features. Demo is basically skin thickness. And here I can go back and just copy the code here and take the column, push it in, done. So demo is already saved. Demo I've not tampered with. So what I'll just quickly go back and load this once again, guys. Okay. Otherwise my data frame is different now. So I'll just quickly load this demo once again. And let's come back here and drop these columns as in replace the nans here. And now demo.info. And you can see the true state of my data right now. Look at this. 394 missing values, non-null values, 757 non-null values, 541 non-null values. Now you might ask me, Sayan, how do you handle this now? In a practical situation, how do you handle this now? You know how I'll handle this? I'll say insulin is anyways a worthless column. So let's not waste time on this. Insulin, let's straight away drop it. Anyways, 50% of my data is missing. Insulin is anyways a worthless column. Anyways, is basically a worthless column. So let's go back and drop that column. Right? Yes. Let's go back and drop that column. So that's it. The point is outliers. Some outliers will still remain. Okay. See the notion that we have that remove outliers is a very incorrect notion. Again, all that is part of theory that we generally hear and study. But the point is, you can never completely remove outliers. There can be good outliers also. Even in a normal distribution, there are good outliers and there are bad outliers. Good outliers are where my normal distribution itself means that beyond plus minus 3 standard deviation, there'll be good outliers. That is okay. That is normally with the shape of my data. Absolutely fine. That is basically what we're trying to achieve. We're trying to basically convert our skewed data into a more symmetric distribution. That's what we're trying to achieve. So we're basically calling it good outliers. Okay. Yes. Hello. We're not getting into domain-based discussions here, but basically based on my data, we are seeing it's not an important feature. So random forest feature importance is it's not important. So we are trusting it's not important. But definitely, I think your point is taken. I would say, like in a way, definitely conversations with the doctor is also important. You need to consult and see, hey, this is what I'm seeing. Is it right? That's definitely important. Yes. Okay. Sir, I think I don't understand where the issue is. Power transformer is outlier imputer is missing value. This is the fundamental crux of what we talked about last time as well. If you're going over the same thing, then we'll not be able to move forward. Okay, we need to be clear with what we talked about last time as well, right? So power transformer is for Gaussian distribution. Imputation is for missing value. Why the hell do you call it impute? You call it imputation because you're trying to impute, you're trying to substitute missing values, right? Isn't it? I mean, why will power transformer treat missing values automatically? Nobody's saying that, right, Ravi? Yeah. Let's get going. Let's get going and let's yeah. Can we drop skin thickness? Well, we'll see that. The RFP technique we'll actually observe. Let's see that. Now I'm just building a iteration 2 model here, as you can see. So we're splitting our training data, testing data once again, and so this is the iteration 2 model that we're doing. There's a small issue you would have seen every time the model performance is 74.67, and you're wondering, hey, Sain, what's happening? Because we're supposed to get a good performance increase, and the reason why this is happening is because I am not doing my XY split after that, right? So the XY is being taken from the previous step. Okay, so I'm just going to quickly show you that once again. Where is the XY split I did here? I'm going to quickly do the XY split from here. And let me quickly show you. So X is this and Y is this. So once I do that, because now now my demo column is dirty. So I take the demo column, I do an XY, this is my X and this is my Y. And on the basis of that train test split, and if you look at the performance, this is the thing that we are getting right now. Okay, this is the thing that we're getting right now as we speak. Now the point is how do we go back? How do we go back and make it better? How do we go back and improve the performance of this right now? How do I go back and make the performance of this model slightly better? How can we do that? Let's see. Let me just take the demo here itself right away once again, so that I don't end up running the same code again and again. I'll just quickly take the demo here itself. And I'm just imputing all these missing values here. And finally, this is the state of my demo data frame. This is where we are looking at from, right? You do your XY split, and it's pretty much what we are observing right now. So keep the outcome separate, keep the Y separate, and the train test split you're doing. And you're fitting your model on train data. The pipeline is what you're building. You're fitting this on your train data, and you're evaluating this on your test data. Okay, that's what we are observing right now. What's that? Yes. Okay. Yes. All right. So now the other aspect that I would like to kind of do right now is I would like to quickly execute the remove the the insulin column also. The insulin column is not adding much value. So maybe iteration 2, I would like to remove the insulin column also. So demo.drop. I would like to drop the insulin column also. So demo.drop insulin and axis equal to 1. Because insulin, as I said, is not a great feature, and also there are too many missing values. So instead of doing it like this, let me just drop the insulin column and in place equal to true. We can say in place equal to true, or we can just write it back to demo itself. So we can drop the insulin column, and now the rest of the analysis flows with respect to that. Okay, so we can try out the next iteration, and we can see what is the performance that we are getting with respect to that. Okay. One more thing I can basically add here, code. Sure, the code is this. Hey, this code I've already pinged, right? No, guys. This code I've already pinged you guys. No, is the code not there? Quick check with all of you. Okay, I'll just quickly ping the code to all of you. This is the pipeline that you can actually build. So I think I can ping you these parts of the code. This is the part that I've done newly. Rest of the things are very straightforward. Okay, nothing new that we have talked about there. Pretty much the same workflow that we have built right now. Score, no change. Yeah, hold on. 1 second. So no, the score will change. This is basically because my XY features are slightly different. I'll show you a notebook where I've just rectified that. Okay, I've just messed up the features here. That's the reason why you're seeing the code is not changing. But try it out. The score will definitely go up quite a bit. The score will go up quite a bit. So blood pressure, and here we are looking at it with respect to insulin and body mass index. And here we are seeing with respect to blood pressure and skin thickness. Okay? Yeah, it'll improve. It'll improve. That's what, yeah, it'll improve. Try it out. Try it out. It'll improve. 100% it'll improve. Yes. You can do it. Categorical data also you can do it. Absolutely. You can do it. You can use it for categorical data also. Okay. Uh, let's get going. Done, all of you. So this is the drop part, and then next thing is the insulin part. Please drop the insulin column. Insulin column is not adding any value to the overall process, so we'll just drop the insulin column. And next thing that we'll do is we'll go ahead and build the pipeline right now. And the pipeline code is something I've already pinged you, right? This part I've already pinged you guys. So please use this. No? Okay. Yeah. Actually, the horde block is not possible, guys. I think there's a limitation in the, I guess, the number of characters. So that's the problem. Right. It allows only 200 characters, right? Yes. Okay. Yeah. Chalo, we'll carry on for some time. You guys are free now. I mean, you're okay, right? I mean, we can go on for like some more time. I think 45, 50 minutes are fine with you. You guys want to take a break or something? You want to take a little bit of time, take a break and come back? Yeah. So I have all the time. So I think we can take a break. We can take a small break. Okay. So take a break. Yeah, no, I can continue, but I guess take a break and let's circle back. Okay, because we can carry on. I think at least until 9:45 types we can continue. Okay. Take a break. Aram se take a break. Maybe let's say 10 minutes. Take a break and let's come back and we'll pretty much do another. Getting some error, Yuvraj. What error are you getting? Import trace back. The way you're ping that error, no, like nobody can read that. Nobody can read that error. What error are you getting? Yeah. No, so you have not imported iterative imputer, sir. You have to impute. You have to import iterative imputer, right? What's that? Need to travel. Uh, okay. Okay, okay, fine. So, okay, yeah, yeah. No, no, you need to import that library. I just pinged you that one, Arindam. Yeah. So Arindam, is it recorded? Yes, the session is recorded. Yes, session is recorded. Yes. I'll not delay you guys for too long. Maybe until 9:30 I'll take along with you. Okay, not too long. 9:30. So in case you guys can stay back for another half an hour, 45 minutes, we'll just great. Okay, so let's take a break. So I'll come back. I'll see you guys in another 5-10 minutes time. Take a break and we'll carry on with the exercise. And we will look at some more aspects of classification. Okay, with respect to that, we'll add in the feature selection part, the RFE part, the feature importance part, and the p-value statistical test part. All of it will wrap into the pipeline. Okay, until now we have got a very basic working pipeline from what we did last time, and now we'll try to add in all the components that we discussed before. So all of those components, feature selection, statistical test, all of that we'll try to plug in here. Okay. So I'll see you back in another 10 minutes. Okay. Take a break and we'll see you back. Yeah. Hey guys, welcome back. Yeah, so let's get going. Many of you were saying that you are not getting the right answers. I'm actually a little surprised. So testing accuracy you're saying is the same. Is it still happening? Check the variables once if you're fitting with the right variables. Check the variables once, please. You should be able to see you should be able to see a good decent improvement happening for sure. For sure, a decent improvement will happen. Yeah. Yes, yes, it will improve. I think from 74 it will go to 76. Correct. 76 is what you're getting mostly, son. Right. 76, 77 is what you will see. 76 point. Right, right. Let me project it. Let me show. Let me show you. Even I made the same mistake. No. Even I made the same mistake. So in the break time, I was rectifying this. So what I did was, I'll show you what I did. I was actually. I made the same mistake. Whatever issue that you are reporting, I had the same issue. Then in the break time, I was actually looking over it a little bit. I think most of you made the same mistake that I did. So again, it's an issue. It's an issue with respect to the XY thing, because see there are so many variables we are creating, right? So I would encourage you to just take a minute, go back to your workflow once, um, and just check it up once, okay? Right. Is there a better way to kind of share this thing with you so that you can do it together along with me? Yeah. Let's see how I can share this with you. Give me a second, guys. I'll create a quick drive link where I'll share this entire file with you. I think that will make much more sense. So together, end to end, we'll collaborate and do. So that will make much more sense than, you know. So let me just quickly create a drive link where I think most of us would have coded the solution until now. And now we'll quickly create a drive link and share with you. Okay. Just give me a second. Just give me a second. So anyways, what I do is after the sessions, I'll anyway share the file. But I think this time, because it's slightly bigger file, and I think the workflow, because some of you are getting that mistake, that error, that's the whole idea why I want to share that file with you. Okay, this will take hardly a second. I'll just quickly create a drive link and share that file with you. Okay? This will take a quick second. So courtesy Google, these things are a jiffy nowadays. So hold on. So I'll quickly go back and download this from my Kaggle as well parallelly. Then I'll share with you. Okay, just give me a second, guys. Just give me a second. Right, that's the initial training accuracy we'll get. You guys are absolutely correct. That's the initial training accuracy we'll get. But the testing will be higher than that. Once you do the imputation, the testing will be higher. That's why I'm just sharing with you once again, just to get rid of the confusion. Initial training accuracy just with logistic will come out to be exactly what you think. But after you do the imputation, the training will increase. It will actually go up. Okay, wonderful. So just quickly share the link. Now the file I've actually is updated now from my end. Then I'll just quickly share the link with you guys. Okay. All right, here it goes, guys. Please access this link. Please access this link. So I've shared a Google Drive link with all of you. You will find the entire Jupyter notebook for the class there. So all you do is go back to the notebook, open up in your local machine or just upload to Kaggle, open up your local, the entire thing is actually solved there, okay? And just take a minute. I would encourage all of you to just take 5 minutes and just run the code once so that all of you are in sync with, what we have seen until now. And then we'll add on to it, okay? Then we'll together add on to it. Take a minute, download that notebook, put it into Kaggle, or you can use your local Jupyter also. I'm just doing Kaggle to get you some practice there, but you can use your local machine also. It will run absolutely fine there. Okay, link is accessible. Just download the code and put it into Kaggle, all of you. That's pretty much the same thing that we've been talking about. Okay, that's a complete code that has been uploaded there. I mean, that's more than what you've talked about. The complete code is there. Can you just head over to the link once? Yeah. All of you, take a minute, please. Download the notebook from there, please, and just run it. Just execute it once. And if you do it correctly, if you do everything that I discussed correctly, you will actually end up seeing, this is what I was referring to. After you do the imputation, no, you will end up seeing a performance of 76%. 76.6 you will actually get. Try it out, run the code, run the notebook the way I've shared with you, and you will see the same answers. Then we can iterate, we can debate and discuss about improvements on this. Okay. Yes. No, it is changing. This is the same thing I've shared with you. No, is this not the same one that I shared with you? Okay. What are you sharing? Same notebook I've shared with you. No, you can see 76.62. No, let me just check which one I've shared. Give me a second. Yes, it is different, right? Oh, this one is different. You're not seeing the same one. Oh, hold on. Give me a second. What have I shared? Okay. Hold on. Give me a second. What have I shared then? Hold on. I think in that case I missed saving in Kaggle probably. Hold on. Give me a second. Sorry, but this shouldn't impact it because what I download should be actually whatever I see. Give me a second. Hey, I think you're seeing it. Yeah, just check it once more, please. Check it once more. Let me just parallelly just put it once again, just so that you know. Give me a second, guys. I think it's not a saved version. Just give me a second. I'll just quickly recheck once again. Okay, just give me a second. I'll just quickly check this up once again from my end. Yeah, because I updated some codes here, and which is why it's coming fine. So the variables were a little mismatched, but I just wanted to reconfirm what I shared with you. Give me a second. I just updated that once again, and just let me just see if it's working fine or not now. Quickly check and let you know. Okay. How to open exactly? 77 is what you're getting. That's what I was expecting actually. That's the thing we'll get. I'm surprised why you guys are not getting the same thing. So that's my point. Um, check it once. No. Open new notebook file upload. That's one of the ways you can do it actually. Yep. Yes. Just check it up once. Just sync your environments quickly, guys. Once. Sync it once from your end. It will work absolutely fine. It will work absolutely fine. You can see. So basically, normal model it will give you 74%. That's what we are getting. Okay. Right. Right. After imputation, this is basically where we are. I'm just going to run the code right now. Demo.info, and this is what we are getting. Okay. So after imputation, what you will get. So after basic imputation, you will end up getting what? What is the performance of the model you will get after imputation or before? So this is the basic way to look at it. Okay, you will see 76%. I'm running the code in front of you right now. Okay, it's 76%. First imputation, then power transformer, then standard scaler. Standard scaler is not required actually. You can remove that. And this is 76%. You're seeing that I'm running the code in front of you right now. Yeah, exactly. That's the thing you will get. Yes. Same answers, Siddharth. Same answers. You and I will see the same answers because the code is the same. So yeah. Okay. So iteration one was 74%. This is iteration one. This is where we started our conversation from. Okay. Iteration one, 74% without any imputation. Iteration two, I did imputation. I changed glucose and blood pressure, and I'm getting 76%. And iteration three, I'm applying RFE technique. RFE technique, 77% with RFE. And then select K best, and then confusion matrix. But I'm going to get into all this. But first of all, important question: are you guys seeing the same answers? Where is the? I think there's some problem. Can you run the code once again? Just sync it and check once again. This is the same code snippet I've shared with you guys. Yep. No. Hold on. How do I check? Yeah. 76 exactly 76. Yeah, exactly. That's what I'm expecting. Same answers we will see. Pipeline, same thing you will see actually. Yes. I think you guys are not using the same code snippet that I shared with you. Let me share once again. Shant, you got it? Okay, good. No. See, packages, no. Accuracy does not depend on packages, Harsha. Accuracy depends on your random state primarily. Whatever random state you have used, it depends on that, not packages. Python version will not impact how logistic regression works. But to some extent, Harsha, I would say maybe for more advanced algorithms, some hyperparameter settings could be different. That is, I will not outright deny it, but to some extent, definitely, the packages might impact some other kinds of models, but not this one. Logistic settings will not change it. You might get a different answer, Harsha, if you're basically using a different random state. If you're saying, Sayan, I want a different data in my test set. My test set is different. Now what will now it will give a different answer, definitely. Okay. Give me a second, guys. I think let me just share this once again with you. I think there's too much of confusion with the link and stuff. You know what? Let me just go back and update this once again and check. Google cannot be a culprit, right? Google will not say no. I'll not update that code. Let me just do it once again for you. Yeah, just so that everybody is able to follow along properly. Okay, can you just check the code now? Can you check the code now? I've additionally vetted it. You can see I'm just opening it in front of you in my drive itself. Okay, just to check, guys. I want to ensure everybody is following along with you. Okay, I'm checking on my drive itself. Okay, you can see my drive, Google Colab. I'll go to Google Colab and quickly open it up for you. Okay, I'll go to Google Colab and quickly kind of open it up for you. Google Colab, and this is the same link that will work for you now. It's absolutely fine. Can you just check once? Just refresh your drive. Take the file once again. Okay. I don't care what you have done, what has happened until now. Just do a refresh once again. People who are not able to get it working, people who are able to get it working fine, you would have probably figured it out. People who are still not able to get it working, just go download once again from the drive. What is the link? Let me just quickly share with you once again. Just download once again from the drive, and you can see this is the thing that you will get. After the imputation, you will all be able to see 76% and 77%. This is what you will actually see. Please check it up once. No, now it should be the same thing. You will get it. The rest of you can also just check it up once, okay? Because I'm not sure what link I maybe mistakenly shared. Not sure. Okay. Just for surety, just go back and just take this fresh notebook from the drive, please. All of you. All of you. I think let's just all of you do this, okay? I think the notebook I shared with you last time was probably not saved. Could be the reason. Okay. Yeah. And the other reason could be that Google Drive update itself takes time because I was updating it periodically. So some of you, the updates reach faster. Other people, updates reached took time. That's more of a Google Drive issue. It's pretty much how the infrastructure works, right? It's all updates are not absolutely instant. The updates take time to see across the network. Anyways, so can you just check it up once now? Just check it up now. It should be working absolutely fine. You should be able to see this thing now. All of you just do a download now. And it should be working absolutely fine. How to upload in? Yeah. The cell below demo info. Which one is that? Which one is that? This one? Which one? Which one? WVES. Sorry, can you just tell me the cell number with respect to this? You mean to say the cell below demo info is basically this one? You mean to say this one? This one? This one, Siddharth? Okay, this is a very manual way of doing power. No, that's beside the point. But that's actually something else. I'll talk about it if you're not. So this is basically a very manual way of incorporating a pipeline. So Siddharth, a normal way to put a pipeline is this, right? This is a very simple way to understand pipeline. Imputation, transformation, scaling, logistics, straightforward. You know, this is a very simple. See, accuracies will not change. Same thing, right down to the last decimal place, accuracies are the same. Pipelines internally are doing this. Okay, that's different. The reason people are confused is because the answers are not matching. That's why I want to ensure that the file that you are using is the same file. Hey, how do you upload it? Is yeah, exactly. Click on a new notebook and file and upload. Uploading a file on Kaggle is no different from uploading a file in your own local Jupyter notebook. So your local Jupyter, the functionality is still the same, right? Yeah. Guys, can I do a final check with all of you? Everybody's in the same file. Are we all clear? This is absolutely fine. I mean, is that clear to everybody? Just anybody else having? Uh, oh, uh, hey, what's that issue? Are you using my same file? Where is that error coming from, sir? Please use my file. Use my file. It should work fine. Yuvraj, just ensure one thing you're doing. Ensure that you are actually adding data. Maybe just yeah. There's no question of error right now because again you're using my file. So please download my file and we'll follow along. Okay. Yeah. Last cell in learning curve demo. Okay, so don't execute that cell right now. Learning curve is a different concept. I think you've not seen this yet. So please don't execute that cell. In case you're worried about that cell right now, the reason why that error is coming, I'll tell you the reason. In case you guys are trying to figure that thing out, the reason why that error is coming is because of this. Again, that's a different concept and the conversation. But just change your variable names here, and it should be working absolutely fine. Okay, so gradient boosting is I think not defined right now, but it should be working absolutely fine. This is basically gradient boosting is not defined. So just set your gradient boosting and it should work absolutely fine. Okay. Take your data. If you just want to get it working up or not, the reason why it's not working is because remember we have added missing values, right? So first you set it back. Just don't worry about the missing values right now. This is a slightly different concept of what learning curves actually are. I'll talk about it right now. The learning curves are a very interesting concept. I'm just loading the data as it is right now. And my x is basically my outcome. Y is basically the outcome. X is drop the outcome. And this is just a different kind of concept that we are seeing. Uh, Learning curves. Learning curves are a very interesting topic. So oftentimes I'm very sure you've faced this question. That when we are building models, how do I know how much data to use? How do I practically figure out how much data to use for machine learning? Right? How do I figure out how much data to actually use for machine learning? So that might be a potential question that will bog you generally. How much data to use in machine learning? And there's no definitive answer to that question generally. There's no definitive answer to that question. So one of the ways to look at it would be you plot a learning curve, and from that learning curve, you basically check how much data is actually required. So this is still executing right now, and you will see there's a beautiful pattern that we'll observe here. And what this tells you guys is, if you look at it, I will ignore gradient boosting for now. That's a different topic. But if you look at this learning curve with respect to logistic regression, it tells you it tells you something about the scalability of your model. That means if I add more records, if I add more training data, how much of additional performance improvement do I end up getting? That's a very interesting idea that you're getting here. So learning curves are very useful to evaluate how much data is required to effectively understand whether your model is training well, or if you need to add some more parameters and stuff like that. So CV is cross validation. That's different. CV is cross validation. So cross validation, Ashok, is like your testing error. So what is cross validation? It's like your testing error. Okay, so Aparna, just to get it working, what you might actually do is just change that class with outcome. This variable issue was actually there. Okay, rest of all will work absolutely fine. Okay, good. So how to interpret the learning curve? Along the x-axis, you have got your number of records. Along the x-axis, you have your number of records. Number of records tell you that, hey, how much of data samples you have. So Bima diabetes, how much of data do I anyways have in my data set? So can we quickly do a check right now? How much of data do we anyways have here? We can quickly do a check right now. Demo.shape I can do for you. How much of data do we have? 768 records we have total. But it's a very small amount of data, honestly. Not a lot of data. Only 768 records is actually very small. We have a very small amount of data right now. And what it means is, it means that, hey, if I train the model with 100 records, I'm getting this much performance. It's overfitting very clearly. And I think we have all learned about this concept. We have all theoretically studied this. This is the way to beautifully visualize it. You can look at logistic. Logistic is a fundamentally underfit model. It's a very basic model, naive model. Logistic regression always creates linear boundaries in the mathematical space. The decision boundaries are always linear in logistic regression. It's always linear decision boundaries you create. Okay. Unlike gradient boosting, which tries to create more complex decision boundaries, logistic regression creates linear decision boundaries. The data set is very, I would say it's pretty complicated right now. It's a very hard classification problem. Logistic is only able to touch around 80%, 76% accuracy, as you can see. Okay. Connection lost. Hello. Can you hear me, guys? Hello. Am I audible to all of you? Okay. Okay. Great. Okay. Great. So what the other thing it beautifully conveys is that, hey, if I have very limited amount of data, the model is kind of overfitting because training score is very high, testing score is very low. Cross validation matlab testing. Overfitting. Even logistic में overfitting हो रहा है. And as you increase your number of records, see, increasing doesn't mean I'm taking 1,000 records and no, increasing means I'm only going up to whatever limited amount of data I have. So when this is only training data, by the way, just to clarify, this is only training data. See right now, let's see, guys, demo.shape has 768. What is xtrain.shape? What is xtrain.shape? Xtrain.shape will be training data samples 614. You can understand this right now. Why the axis is ending at 600. There are only 614 records in my training. We always evaluate the performance of our models on training data, right? So that's what I'm evaluating right now. Hey, if I give only 100 records in training and build a model, this is the performance I get. 200 records build a model, this is the performance I get. 600 records and build a model, this is the performance I get. It's kind of converging. But the other beautiful aspect that you're seeing right now, the model is kind of going up. There's an increasing pattern, which basically means that probably if I include more data samples, the learning power is still high. Maybe the model can still learn more. That's the other aspect that you're learning from this. Logistic, the curve is still kind of going up. So that means if you add more records, right now I've got very limited amount of data. Only 614 records in training. First of all, it's a very hard data set. The feature quality is not great. You've got very, very poor quality data. And even the number of data samples are also less. This curve actually gives an indication to you that if I increase the number of data samples, maybe the learning power of my model can actually increase. That's the intuition that you're getting from this particular learning curve. It's a very powerful way to evaluate how much data is required. Machine learning is always a game of trade-offs, right? It's not always about accuracy. Accuracy is only, in casual competitions where you're always trying to go for the best performance and stuff like that. Production level implementation is a lot to do with, I would say, how did, Harsha, let me share this once again with you. I think this is only one piece of code I have to share. I think the final notebook where we'll have this thing. Okay, don't worry. So production level implementation, basically what we'll have is we'll basically have to consider the time component also. We have to consider the time component also. How much time the model actually takes. And this gives you an idea of the amount of time. See, gradient boosting, there is no comparison. Definitely the performance is better, and you can clearly see the learning power is also very, very high. I think most of you have seen a bit of boosting in your classes. You can understand that when number of records are 100, the model is highly overfitting. At least when I increase my number of records, at least the model is kind of converging. So gradient boosting, the power is much, much higher. So if you increase your number of records, definitely the learning power is very, very high comparatively. The other very interesting aspect I like about this curve is the scalability. Not only does it tell you with respect to examples how the accuracy increases, but it also tells you the learning time. And you can see very clearly the logistic curve, the way it kind of converges. It gives an idea to you that, hey, I mean, if I include more examples in my data, the computational complexity also increases in a way to some extent. It gives an idea about the computational complexity as well. And finally, to combine this and this, we have this curve. And this is what gives you a very good picture. I would say an excellent picture that both the models are kind of conveying to you that, hey, we both have a lot of learning power left. That means it clearly tells you that the number of records are insufficient. The number of records are right now insufficient for the modeling purposes. We can learn further. We can learn better. So give us more data points, we can learn better. You can clearly see the increasing peak, the linear pattern, the linear trend. That means for x-axis is fit time, y-axis is code. You know what kind of a curve I would like to see here? Here, I would like to see a curve that looks somewhat like this. And I'll straight away take you to sklearn documentation of learning curve and validation curve. The kind of curve I would like to see here, this is the same documentation with respect to learning curves in sklearn. Very, very interesting. It's a very important topic actually. Right. So this is a learning curve and validation curve. See, when I'm explaining, don't run the code along with. Then otherwise you will not follow what I'm talking about. Makes sense, right? See, when I'm explaining the concept, there's no point in running code. Okay. Look at the explanation. The code there is worthless actually. There's no worth in the code. The code is to copy paste. So that file I'll anyway share with you, Vikram. Don't run the code right now. You understand the concept, the code you can run later. Okay. All right. So now this is only the last cell of code I'm yet to share with you. So that I will share with you in the final notebook. Okay. Don't worry about the code. So look at this. This is the ideal thing I would like to achieve. This is a slightly different implementation these guys have done. Okay. This is the ideal thing I would like to achieve. These are two different model comparisons you're seeing. This is the ideal thing I would like to achieve. Because this is what tells me, this is a different data set by the way. Okay? This is what tells me that, hey, you know what? For every unit increase in time, the accuracy kind of remains the same. This is a different data set, not diabetes, by the way. For every unit increase in time, the accuracy kind of remains the same. The trade-off is what we are talking about right now. 1 unit more it takes to train, the accuracy kind of remains the same. So it's kind of the cost benefit analysis we are discussing right now. So is it worth? So I've already trained the model with, let's say, 1400 examples. I've already trained the model with 1400 examples here. Is it worth adding another 200 examples? Will I get a major performance boost? Answer is no, because the model fit time will increase. The model fit time will increase by, let's say, 2 milliseconds, but the scores will kind of remain the constant. So this kind of a thing, if I see, I think that's the point when I say, okay, I need to stop. I need to stop. And this is actually right. This is right. This is always I would say this is always going. There's always a scope for learning, Ravi, but the conversation is always on the lines of trade-off. I mean, how much can you learn anyway? It's like saying if you so I'll give a hypothetical analogy to you. If you have learned until, let's say, 12 o'clock midnight, let's say the class goes until 12 o'clock, you've already learned so much. Beyond the point, every 5 minutes we spend, the performance will not go up. Performance will be stagnant. So that's the way. So beyond the point, it's more like, as I say, it's flogging a dead horse, as they say, right? The horse is already dead. You can't do anything more with the horse, right? The model, you have already extracted the last juice from the model. There's nothing more you can get out of it. So, and this actually helps us, I would say, this actually helps us get to a very important concept in machine learning, that just adding data is not enough. Just adding data is not enough. Even adding good quality features is important. Right now, the conversation we are having is only adding features, only adding data. Should I add more data? No, that's not enough. You need to add good quality features also. Add good quality features also. That's important. That's an important conversation. Add good quality features, make your model powerful. Both are important factors. If you only say, no, Sayan, I will add features, but not enough data, that's bad, overfitting. And if you say, no, Sayan, I will add a lot of data, I'll give you a lot of sample data, but not good quality features, then also is bad. I mean, imagine a scenario where you're saying, I want to model stock market, I want to do stock market prediction, or I want to predict diabetes. I want to predict diabetes using day of the week. I mean, what prediction can you do with that? Or customer level of detail, I want to predict diabetes based on your race, or based on the color of your skin, or the color of your hair. That doesn't make sense, right? So you have a lot of data. You give me 1 million samples of data, 1 billion samples of data. What will I do with that? There's zero correlation between the two. So this is the intuition behind it. Beyond the point, just adding features will not help you. Just adding data will not help you. You need to add good quality features also. That's the way to look at it. Okay? I hope the idea is clear to you. Yeah. I would say you can think of new enhanced models, Ravi, but I think we are already exploring one of the most powerful algorithms out there, which is support vector machine. But with support vector machines also we are reaching this performance. So that's why I would say the model will not increase any further, because they're already touching 100% accuracy. This is a different use case. We are not talking about diabetes. I just took you to a different documentation right now. This is a different use case. You're already touching 100%, close to 100%, but beyond this you cannot learn further. Does it make sense? You're seeing the curve right now, Ravi? Yeah. I think this should answer your question. Okay? This is naive based. Naive based is a very basic, very naive algorithm, very basic algorithm. But support vector machines are very, very powerful. They're giving you almost around 99.9%. Beyond that, you can't learn any better. Now, taking the conversation forward to diabetes, what we are looking at right now in our context, right? So, see, once again, we are back to the code, guys. See, so Krishna, hold off. Don't worry, okay? Don't worry about the code. The code is worthless, okay? There's no worth in the code. Code is 2 minutes. Okay? I'll share the notebook with you. Don't worry. This is only one cell that we are talking about, right? The end first. Just understand the concept. The code I will share with you. Okay. Now, coming to this one, it tells you that if you add more records, the learning power will basically increase. The learning power of the model will basically increase. So that's the intuition that you're getting here. That's the final curve that you're seeing right now. And in case you're wondering, what is this shade? What is the shade right now? What is the shade all about? Who will explain to me? What is the shade right now? The shade is cross-validation, standard deviation. Because we're doing cross-validation, right? Inside the learning curve, we're doing cross-validation. These are your median accuracies, average accuracies, or the average scores, average fit times. These are the cross-validations, the standard deviations. So the band kind of gives you some kind of a confidence interval to work with. That's the intuition behind what this means. Okay. Hope this is clear with all of you. Hope the concept is absolutely clear. It's a bit of an advanced concept, but I think you should know it. You're studying ML, so you should know it. Similar to learning curve, there is also something else called validation curve. This is the conversation probably part aside for a more advanced session, but similar to learning curve, you also have something called validation curve. This is also very interesting. Validation curves actually help you understand. Validation curves actually help you understand the effect of hyperparameters on your model. So with respect to decision tree, it kind of means that number of estimators and score. That is the thing that we are looking at right now. X-axis number of estimators, how many trees, and y-axis score. This is something that you have heard about countless number of times, right? Model accuracy curve. But how do we plot it? Generally, I don't think you've plotted this kind of thing before, right? How can you plot it easily? You can plot it using validation curves. You can easily plot it using validation curves. Code is one line. Use model validation curve, and you can plot out, the impact of your hyperparameters on your model. How can you plot it out? How can you visualize it? That's an important way to look at it. And I'll tell you why this is important. The other aspect why this is important. The reason why this conversation is important is because it's not always grid search CV. When you're working across a whole range of models, it's not always grid search CV that matters. Okay, grid search CV is one component that is involved here, definitely. But everything is not grid search CV. Grid search CV will not help you to see the flow like what you're seeing right now. By looking at this, you can clearly say that yes, when my estimators are less, that means let's say estimators means number of decision trees. Think of it like a boosting or a bagging kind of model. If the estimators are less, then underfitting. If the estimators are more, it's overfitting. Think of it that way. Okay, but this is basically how we can visualize the learning curve. Yeah, don't worry, Narsimha. We actually went into some more advanced topics. This is not part of our conversation, but I think for some of you, I wanted to introduce these topics. This is validation curve. Okay, yeah, don't worry about this right now. Okay, great. Let's come back and let's go back to our code sample once again. Okay, yeah. All right. So where is our logistic? Yep. So what I will do here, remember in our very initial conversation, we were discussing about the specifically about the, hold on. We were talking about the the coefficients. Let's see how the coefficients impact us here. Let's see how the coefficients specifically impact us here. I'll go back to the basic initial iteration model once again for all of you. Okay? Basic model once again. I'll go back right now. And what I'll do is I'll quickly go back and look at the coefficients of my logistic model. So how do I explore the coefficients of my logistic model? So whenever you have something in a pipeline, okay. So what is the meaning of coefficients of a logistic model? How do you explore the coefficients here in the code? Okay, so I can simplify this. This is actually not required right now. I think we have already discussed about pipelines, so we understand what pipelines are. Let me simplify the code a little bit just so that we can focus on the core part right now. So I'll just quickly use a logistic regression model here. That's my logistic regression model. And I want to show you the conversation that I want to have with all of you right now is, in a way, the coefficients of the model basically. Okay, anyways. So guys, one important thing here is how do you access a particular step of a pipeline? Because typically for a logistic model, there is something called lr.coef underscore, right? There is something called lr.coef underscore. You can visualize your coefficients, right? Guys, just to clarify, whatever conversation I had 1 minute prior to this validation curve, please ignore it. Okay, that's a very different thing. Okay, please ignore it. I want to ensure at least learning curve everybody got. Validation curve was not relevant to our conversation right now. So maximum depth and estimators are a very different thing altogether. But I just wanted to ensure everybody understood this. That's what I wanted to ensure. Validation curve is a very different thing, which we went into through the flow of the questions that were asked. That is not a topic that I want to take over everybody right now. Okay. All right. So please do not worry about that right now. Validation curves. Now, so coming back to the thing, how do I print out the coefficients of my logistic model? How do I specifically print out coefficients of my logistic regression model? How do we print this out? Coef underscore. If I run this piece of code, you'll get an error specifically. Here you're getting the thing because error is actually, you have already executed it somewhere. If you remember previously, I already executed a lot. Okay, but what if I use a different piece of code? Let me show you. Let's say I use a piece of code called log or logistic. Let's say I call it logistic. Can you simply say logistic dot coefficient? Will it work? Let's say I run the pipeline here in front of you. I run the pipeline and I run this piece of code. It will give error. Logistic is not defined. Although you are having logistic happening here, sir, once again, see, if you can just follow along what I'm explaining, Vishal. Learning curve वो 2 line का code है, उसपे don't waste your time. That's just a simple thing. I'll ping you. That's what I'm saying repeatedly. Don't worry about learning curve, sir. 2 lines of code. Okay, just observe what I'm explaining right now. All right. Yeah. So if you do logistic.coef underscore, what will you get? You'll actually get an error because you have not fit this model. So how do you access an intermediate pipeline step? Again, we are learning a slightly different concept right now. Whenever you're trying, how do you access an intermediate pipeline step? Pipeline intermediate step, how do you access? Anybody? How do I basically access that intermediate pipeline step? How do I access the logistic? Because otherwise, coef underscore, how do I print, right? Yes, name step. Very good. Shubhendu has put the right answer. We say something called name step. So we say pipe.name steps, pipe.name. It's like a dictionary right now. It's like a dictionary right now. You say pipe.name steps, and then within bracket, it's almost like a key value pair. Within bracket, you say logistic. When you do that, you actually get to see that logistic regression right now. Now there goes my classifier. You want to see the type of that sklearn, that Python object. What is the type of that Python object? That's a sklearn linear model logistic regression class object. That's what you're seeing right now. Now, once I have this, with that, I can go back and print out my coef underscore right now. I can print out my coef underscore right now. Sorry, coef underscore. Okay, coef underscore. This is what I can print out. And this will give me something very powerful. This is what our next conversation will be about. Okay, so what have I done? We have a pipeline. This is the same thing we have seen before. Just look at, just focus on this part of the screen. This part I'll ping you guys. This part I'll ping you guys. This is just name steps. All that we are talking about is, hey, how do I access the intermediate steps of a pipeline? How do I access the intermediate steps of a pipeline? Now, once you do this, my next question that is directed at all of you, how do I interpret these coefficients? We learned about coefficients. We started our session with, logistic regression, 1 by E plus, all those things. We saw logistic regression. Now the question is, when you look at these coefficients, how do you interpret the coefficients? Specifically, let's focus on one of these coefficients. Let's say 1.03. How do we interpret this value in English? Let me hear from all of you. What is the, and specific? I don't want any generic answer. I want specific answer. What is the interpretation of this in English? Just like in linear regression, you say 1 unit increase in this leads to this much unit increase in this. Similarly, I want to know, how do you interpret the coefficient of a logistic regression in English, just like you do for linear regression models. Okay? Think about it. Think about it, all of you. And this will lead us to another very beautiful concept from here onwards. No, rather again specifics. Not generic answer. I want specific answer. How much increase? What increase? I want a very specific answer. No, you're right. I'm not denying you're wrong. You're right, but I want a specific answer with numbers. With specific to this variable, I want specific answer. Not correct. You're not absolutely log. Okay, again, it's proportionality and all that. I want specific. How much increase specifically? Okay. Take a minute if you want a piece of notepad to write it down. Take a minute, all of you. And why is it important is because this leads you to how you can understand the importance of a particular feature, which is where we started our conversation from, right? We are trying to study how is a feature important, right? In a classification problem, generally, how do you evaluate the importance of a feature in classification? How do you generally understand the importance of a feature with respect to classification? That's what you're getting right. Then the value of that variable increases in 1 unit will cause 1.03 units in probability of y. Log odds, e to the power 1 by 3. Okay, you can also interpret this in terms of log odds. So if I quickly highlight that equation, right? If I quickly highlight that equation, guys. So remember, what was the equation that we learned some time back? Log odds is equal to m1 times x1 plus m2 times x2. So this time I'm just going to rest it out separately. M2 times x2 basically means 1.03 times glucose. I'm going to list this out as it is, okay? Plus dot c. Okay, this is the way to look at it. This is a logic regression equation that we have, right? Log odds is equal to m1 times x1 plus m2 times glucose plus m3 times blood pressure plus m4 times diabetes pedigree function and dot c. That's what you have. Now, what this means is, for 1 unit increase in glucose, which most of you have already answered it, I'm aware, which is good that you have followed it, good. 1 unit increase in glucose, the log odds goes up by 1.03 units. The log odds goes up by 1.03 units. 1.03 unit increase in log odds. Right? So 1 unit increase in glucose, the log odds has increased by 1.03 units. And what this effectively means is, if you just translate the whole thing, now we are trying to understand that, hey, Sain, what is this? I'm going to use a different color. It's like, what is the meaning of this what is the meaning of this 1.03 increase in log odds? How do you read this right now? How do you read this right now? So 1.03 is the increase in log odds. I'm just separating this out. Now what you do is, you take e to the power, exactly, increases by e to the power 1.03 times. Beautiful, yes. So you take e to the power 3 both sides. You raise it to e to the power both sides. That means e to the power 1.03 of odds. So this translates to e to the power 1.03 increase in odds. So effectively, it's kind of 2.73 times increase. E is basically, it's a number higher than that, correct? E is the Euler's constant. E is the Euler's constant, which is basically 2.73. And what it tells you is something very powerful. Remember, I started my conversation saying that regression models, especially linear models, when you talk about linear regression, logistic regression, these linear models are primarily used to study relationship between variables. Relationship between input output, relationship between features. You're trying to study that, and this helps me study right even before I model my problem for prediction purposes. Prediction comes much later. If I'm purely trying to study the relationship between glucose and diabetes, this actually helps me study that relationship very effectively. I can see that I can see that 1 unit increase in glucose leads to a very high increase in diabetes. That means glucose is a very strong predictor of diabetes. This is exactly the same conversation we were having with respect to feature importance. Now you can see all these are leading me to the same point. You can see very clearly glucose is the strongest predictor. The next strongest predictor is basically body mass index, and the next strongest predictor is age. Right? So I think this is beautiful, because all of these things are leading me to the same conclusion, that these are important features. And now I actually get more confidence building a model with respect to these features. So feature selection is not something that you do with only one kind of technique. Feature selection is something that you do with a range of techniques. So this is also kind of acting as a feature selection for you. It's helping you to understand, hey, I think this feature is more powerful in helping me predict diabetes. Because if I know the glucose increases by this much unit, the diabetes goes up by this much unit. So the odds increases by so much also. So all of these are leading me to the same direction. Okay, is it clear? All of you are with me on this? Does it make sense? You're able to connect the dots, feature importance, key values, and this makes sense from that perspective. All of you are able to connect. And this is how logistic coefficients can be used for this purpose. Logistic coefficients can also be used for this purpose. This is again very different. I mean, we don't use coefficients for doing this, but Beautiful. I mean, logistic was now one thing I must highlight, guys. One thing I must highlight: you have to scale your data. Very important. People often have this question that should I scale my data for linear models? It's a very question that usually comes up. That should I scale my data for linear models? Generally, scaling will not improve the performance of your models. Whether it is linear regression, logistic regression, scaling will not improve your performance. Whether you scale your data, don't scale your data, it will not improve the performance. But scaling is mandatory for doing this kind of work. Remember, if you don't scale your data, 1 unit increase in glucose will give you very different answers here. You want to quickly see a demo of that? I'll quickly show a demo of that to you, and I'll prove it to you why scaling will not impact your will negatively impact this model. But before I erase the screen, is everybody clear with this? Sure, all of you are clear. This is coefficients of logistic. Does it make sense, all of you? So quick check. Anybody wants to repeat any one part of it here? Is it clear? Exactly. Coefficients will change based on weight, and that's why scaling is mandatory. Scaling will not improve accuracy. Remember, precision, recall, F1 scores, these are all classification bread and butter metrics. They will remain the same, but scaling will definitely help you interpret the coefficients better. Okay, so iteration 2, what I'll quickly do is I'll just do the same thing, but this time I will remove the power transformer part. Okay, I will not do this. So let's say I'll not do any of this stuff because transformation is anyways doing scaling internally. Let's say I'll only do this, and now I'll look at the logistic coefficients based on that. Let's see what happens. So I have my x and y's. Same thing I've done. Okay, same thing I've done, and you look at the thing right now. If you observe the patterns right now, look at this, all of you. Observe the patterns right now. You will see. Look at this. 1.15. What is that feature? Take a guess. That feature is 1.15. You want to see what that feature is? Let me show you. Explain. Let me show you what that feature is. That is diabetes pedigree function. It's a worthless feature actually. It's a worthless feature. Now you take a guess why the coefficients are so high. The coefficients are very high because I have not scaled my data. Because the value itself is in decimal points, it has higher weightages. And this gives me a very incorrect view of my coefficients. So next time anybody asks you, should you scale your data? I mean, so generally this is a very common question and typically something that many people have a question. People are still confused about it generally. Remember, scaling in certain types of algorithms are absolutely required. For example, KNN models and clustering models, distance-based algorithms is required, mandatory. For linear models, linear regression, logistic regression, scaling is mandatory. Scaling is required, I would say, from the perspective of interpretability. If you want to interpret your data, then scaling will be. Yes. Nassima, we're almost done. I just put some closing touches. We're almost done. Don't worry. So scaling will not improve your performance, but scaling will definitely, yes. Scaling will definitely help you interpret your features. You can see very clearly, I did not do scaling right now, and I'm getting wrong interpretation. Interpretation will actually suffer. Interpretation is the only reason why you use logistic models. Otherwise, logistic regression, linear regression is worthless in today's context. Today's context, from a predictability point of view, you will not worry about logistic and linear today because there are better models out there. Primarily, we do these kind of techniques to understand our data, to understand the relationships of our data. And if that is not coming out, then what's the point in using this technique? So that's why scaling is required. Otherwise, not for performance gains. Okay, just to clarify. Okay, so it's just a small iteration I wanted to do with all of you here. Okay. Now, generally that's a interesting question. So will scaling work for tree-based models? Tree-based models are immune to scaling generally. Addition tree, random forest, I would say, tree-based models are immune to scaling generally. Yes. What if explain comparatively with other coefficients? What? What's that? Explain comparatively with other coefficients. No, I mean the interpretation itself is faulty. So this I anyways cannot do it. But I think Ravi, if you mean to say that can I interpret this with respect to other coefficients? Yes, I can. That's what he did, right? So 1 unit increase in like glucose leads to a very high increase in odds, but 1 unit increase in age leads to a very less increase in odds. So that's how we can compare. So higher the coefficients, the more important that feature is in predicting diabetes. That's the way to interpret this whole thing. Okay? Yes. Value of a coefficient, Rama. So Rama, just to clarify, exactly. No, see, that's a different thing, Sant. I think let's hold off on tree-based model. Tree-based is a very different conversation. I think we have a decision tree session planned. We'll have a conversation on that. That's a different thing. let's hold off on that right now. Rama, you had a question with respect to so can so how does model coefficients impact model complexity? Remember, logistic regression models are fundamentally underfit models because the decision boundaries that you end up getting are linear decision boundaries. They're fundamentally underfit models. They are anyways very basic underfit models. So it is not so it's not that if coefficients are high, the models are going to become overfit. Not really. There are ways to control that. If you reduce the coefficients, that's the whole idea of regularization. Okay, but that's a conversation that we are keeping aside for another session, and we'll discuss that in detail. Lasso, ridge, and the C value. So specifically, if you want to explore, you can explore the C value. But anyways, I'll have another detailed discussion with you on that. Okay? But just to give you some insight on that, but I think you got what I'm trying to convey. Just like in linear models, linear regression. How do you look at linear regression? If the coefficients are very high, that means there is more leeway to kind of learn. But in regularization, what you're trying to do is you're trying to make your coefficients smaller. The coefficients become lesser. So the same idea in logistic also. The coefficients will actually become lesser. So it's a fundamentally underfit model, and now we can basically regularize it even more. That's the whole idea. But generally, as I say, these are not very practical techniques. Practically, I mean, it's a theory, it's a topic that we have generally, but many of these things are not so relevant in today's context. So that's the other aspect of it. Okay, let's come back and let's look at one more aspect of our thing here, the final confusion matrix. And I'll have lots of questions for you guys here. Okay, just to clarify, this is your RFE technique that we talked about, right? You have all learned about RFE. You can see with RFE technique, what is the performance gains I'm getting. You can clearly see that, right? Quickly take the code from here once again. Okay, you can all see right now. So what I've done here, RFE. Now I'm putting this whole thing in a pipeline. So what I'm doing right now, I'm putting this whole thing in a pipeline. Iterative, power transformer, scalar you can actually ignore. RFE, I'm using logistic n features to select 3, step equal to 1. Why 3? No reason. It's a hyperparameter. It's a hyperparameter. I can put it in the pipeline and it will do magic basically. Because I don't need all features, guys. I don't need all the features. Because anyways, I know 3 of the most important features. I already know it. What are the 3 most important features? I know it. I already know what are the 3 most important features. I know their glucose, their age, and their body mass index. So RFE will select those features. So I don't have to select all the 8 features, because if you select all the 8 features, it will be overfit model. Maybe the performance will go down. If you select only one feature, what will happen? Underfit model. If you select only one feature selection, you're saying out of 8 features, I will select only glucose feature. Then you're capturing very few patterns. Underfit, very simple model, right? If you select all the features, overfit. Now you're selecting something in between. You can ask me, Sayan, how do you know 3 or 4 or 5? Grid search CV. Whatever grid search CV you have learned in a normal supervised learning context, it can be beautifully integrated as a pipeline. You can integrate that grid search CV as part of a pipeline. You can learn all these hyperparameters at a stretch. Okay. You can do it. Yeah, you can do it. But logistic, we don't have any parameter, hence I'm not showing you. But in a tree-based approach, later on we'll see grid search CV there. Okay. Maybe it's more relevant for a tree-based approach. Here it's only one hyperparameter here. You can try it out. Now, can I apply select k-based? We learned about select k-based. I'm going to show all the 3 feature selection approaches right now. And this is the beauty of using these approaches, because now, see, normally feature selection is a very manual process. You would have studied in a very manual process, right? But now you can see you can plug it in a pipeline. So first step, we are using RFE. Get me the top 3 features. Next step, we're using select k-based. Get me to the top 3 features. How will you select the top 3 features in select k-based? Based on p-values. Straight away, p-values. We've already learned that. If you want to quickly see this thing, again, same answer. Right down to the last decimal place, same answers. You know why they're the same answers? This is RFE, get me the top 3 features. Select k-based, get me the top 3 features. Take a guess why they're the same answers I'm getting. The reason is because in both the cases, I am selecting the 3 same features. That is glucose, body mass index, and age. Because we have seen all this while that those are the 3 most important features. So again, just to show that feature selection technique is also like an ensemble. You try out multiple techniques, and if a feature is a good feature, all the techniques will converge to the same results effectively. And if you want to access this pipeline step, you can do it. You can probably say 5.5 name steps. You already saw that. Now, if I want to extract that particular if I want to extract that particular step, let's say if I want to extract what is that SKB step, and if I want to find out that, hey, please tell me what are the corresponding P values for that particular step, right? So what are the corresponding P values for that particular step? You want to learn the P values for that particular step, you get the same answers. Okay. This is the way you learn the P values for that particular step. Okay. So that becomes a more comparative analysis chance. So if you're getting different answers, I would say it's a more comparative analysis, and that now it's a matter of choosing which technique is more reliable. I would say from a reliability perspective, the most reliable technique is going to be the feature importance technique. The feature importance technique. Okay, the feature importance technique is what you use to evaluate your the most important features. So even RFE is better technique in a way. So this is the univariate statistical technique. If ANOVA test is what you're applying, this is I would say in a way more nice technique. If at all you're getting a close match, then I would say you're better off using an RFE technique. Why RFE? Because I would say use an RFE technique in a way because overall it's a better technique overall. It's a model-based technique because you're building a model and you're learning the parameters based on that. Okay, that's one of the reasons behind it. Yes. And finally, coming back to the aspect of the confusion matrix right now. So what does the confusion matrix tell you? So quick check with all of you in the confusion matrix. How do you read the confusion matrix right now? Question for all of you. How do you read the confusion matrix right now? We're almost done, Krishna. Don't worry. We're almost done. I think another, I would probably say maybe another 5 more minutes I'll take maximum. Yes. Yeah. What about manual feature elimination after RFE? So Ashok, the whole idea of putting it in a pipeline is you're not going to do it manually. Okay, that's the whole idea. So you're putting it in a pipeline and doing it. So again, I'm trying to get you away from that manual stuff right now. Now that we have seen a pipeline, everything you can fit in a pipeline. I mean, the whole thing becomes automated. Okay. Yeah. So no, we understand that. My question is not what is precision, what is recall. We all know that. That's not my question. My question is, what is the interesting thing that you're seeing here right now? What is the thing that's coming out right now? Something interesting that you're able to observe. Again, my question is not what is precision, what is recall, what is confusion matrix. You know that. My question is, what is interesting that you're observing right now? Something interesting that you're able to observe. That is striking you a bit with respect to the domain, the context, the diabetes use case. Okay, non-diabetes has okay, which means what? Not able to highly predict diabetic patients. I think. Would you like to use a better jargon for that, Rajat? I think you're trying to you're getting. I'm understanding what you're trying to convey, but I'm just asking you to use a better jargon. Precision is low. Okay. Let me ask you first of all this question, guys. It's a diabetes use case, it's a medical use case, right? Which error is more? What is more important? Should precision be maximized? Should recall be maximized? Question for all of you. In a medical use case, should recall be maximized? Should precision be maximized? Which one should be high? Should recall be high? Should precision be high? Is it recall or precision? Recall, very good. Recall should be high. Absolutely. Recall should, there's no doubt about it. Recall has to be high. Recall high basically means, recall high basically means from a contextual perspective, recall high basically means that's your, so that's your false positive. That's your false negative. I would say recall high basically means false negative is unacceptable. False negative should be 0, and that means recall should be maximized. So false negative should be minimized and recall should be maximized. That's a medical use case, right? False negative basically means what? Model predicted you don't have diabetes. In reality, you do have diabetes. We are having 22 false negatives. It's the other way around. We got to do a better job to get our model up and running. It's not happening right now. It's a very basic, it's a very naive algorithm that you're looking at right now. Logistic, there's not much we can do out of it. That's the nature of our algorithm right now. but we can definitely use a more powerful ensemble technique to get it better. That's one of the reasons why ensemble models are used. Okay, purely from a predictability perspective, logistic will take you nowhere because logistic will suffer from these kind of issues. So right now my recall and I'll tell you the area where logistics suffers the most, the area where logistics suffers the most are those parts in the decision boundary, are those parts in the decision boundary where there is very highly overlap happening. When the overlaps are very high, that is when logistics suffers the most generally. Because when the overlaps are very high. Because logistic is a very linear decision model, right? Very linear, very basic naive algorithm. So it's a linear decision boundary. So it is unable to learn those very complicated overlapping patterns happening right at the decision boundary. It's unable to make it out. That is exactly where this error is coming up, which ensemble models are much better at discovering. So again, from a medical use case perspective, model predicted negative and person actually has the disease is unacceptable. So recall has to be maximized. What about false positive? Some of you are thinking about balance. You're absolutely correct. Balance has to be maintained. But I would say in a medical practice, false positive is acceptable. It's okay. I mean, it's kind of like saying that model predicted you have the disease, but in reality you don't have. It's an accepted medical practice because doctors do not want to take a risk. I mean, put yourself in a patient's shoes. You go to a hospital and you say, I have this disease. The doctor will be glad to give you 100 tests. Go do this, that. Even he is not sure. Go do this, that, this, and we want to be absolutely sure you don't have this condition. That is accepted. Model predicts, so the doctor thinks that you might have this, might have this, might have this. I don't want to take any chances. I want to basically go back and order all the tests. False positives. False positives are everywhere. Coronavirus. Okay, the way the quarantine is happening right now, if you are infected, your entire house will be sealed off. Think of it that way. False positive use case. So the authorities think you're tested positive. In reality, you're not. They're trying to prevent. It is like prevention is better than cure. Think of it that way. Okay. Right. Coming back to the more the initial question I asked you guys. I think a few of you answered this question already. What you're observing is that, right? What you're observing is that exactly, it is contagious recall, exactly. Its prevention is better than cure, correct. So what you're observing here is that the F1 scores and the precision recall across the board are very low for diabetes. My question is why? That's the pattern that you're observing. For diabetes, the numbers seem to be very less. The recall is also low, precision is also low, F1 score is also low. So what is the reason behind that? Anybody? Very good. Data imbalance, correct. There's a fundamental data imbalance. We call it imbalance classification problem. How do you basically do that? You can actually do a round of oversampling for it. SMOTE, correct. You can use a SMOTE kind of technique to resolve that issue. Okay, SMOTE can be used for oversampling. Right now, see, machine learning is all about machines learn the same way humans learn. Machines learn the same way children learn. If you show the machine less examples of this kind of data, you're showing the machine very few examples of this. You're showing the machine very few examples of this data. The machines will not be able to learn this well. Okay, the performance is very bad right now because I'm giving you 5 examples of not diabetes, but only 1 example of diabetes. You will not be able to learn the diabetes patterns that well. That's the fundamental issue happening right now. So I will do a round of oversampling. People in this audience who do not know oversampling, I'll quickly give you one example. Stratify is not going to oversample your data, Shibandhu. Stratify is for a different reason. Stratify is to maintain the same proportions. So Stratify will not resolve oversampling for you. Make sense? Stratify is more to ensure that whatever proportions you have in the training, the same proportions of classes happen in the testing. But if the class itself is 80-20 split, then the Stratify will not actually help. You got it right. Okay, so this is one of my favorite blogs, Machine Learning Mastery. It's a wonderful blog. They have talked about oversampling here. It's a wonderful topic actually. So you can quickly take a look at it. Again, this is algorithm agnostic. It doesn't matter what algorithm we are using. It's algorithm agnostic. You're seeing this picture on the screen. This is pretty much like what we are seeing in diabetes right now in our class. Okay. So the orange points correspond to diabetes and the blue points correspond to not diabetes. Okay. The orange points correspond to not diabetes, diabetes, and the blue points correspond to not diabetes. There are very few examples of orange. If you try to build a model on this data, remember what does classification models try to do? Classification models fundamentally try to create a decision boundary. Classification models are fundamentally trying to create a decision boundary. That's what the classification models are trying to do. If you have such a limited amount of data, I cannot learn anything. I'll basically try to create a decision boundary like this. Because that's what the separation I'm seeing. I'll give more priority, more weightage to my blue class. I have very few orange classes, right? I don't even care about the orange points. I'm only learning from my blue points primarily. I'll try to separate my blue points perfectly. Orange, I don't care. Some mistakes happen here that I don't care. But blue points, I will try to do very well. That's a general notion in which all models try to learn. Okay. Now coming to what happens after you do SMOTE. SMOTE is an oversampling technique. Okay. So what SMOTE basically does is SMOTE artificially create points like this. So what was previously looking like this, code is 1 or 2 lines of code you have to write for this. Okay. What was basically looking like this before, what through SMOTE what you're doing is you're artificially adding more data points around this point. Okay, so you have this particular point here. You're artificially adding more data points around this point. So now your final data point looks somewhat like this. And now on this data set, I'll tell you what happens. Some couple of things will happen right now. Now when you're building your logistic regression model, the logistic regression model will kind of give equal weightage to both oranges and blues. So now previously the model was looking somewhat like this. Now the model will at least try to separate it out better. It will try to look like this. It will try to do equal mistakes in both blues and oranges, and it's going to come up kind of do the prediction of the oranges a little bit more accurately. That's the intuition behind how SMOTE is trying to rectify the performance of your models. And this is beautifully demonstrated. You can just look at the code; it's beautifully demonstrated. They've talked about the the AUC chains, and you can see right now before SMOTE the performance was very poor, and after applying SMOTE the performances have actually gone up drastically. You can look at the numbers right now. If you go down, the numbers are actually explained. So the ROC AUC scores were only 0.76 generally before SMOTE, and after applying SMOTE, the ROC AUC scores have gone up to 80.81%. So that's a significant improvement I'm getting, and you can take it to 83.4 with a little bit more additional components. Okay, so this is just an amazing technique that we can use like this. Okay, okay. So I would say the only way to generally right. So the only way to basically go about doing this is to keep yourself involved. And I would say quite unlike the domain, and my only guidance is machine learning is a highly unstructured domain. And I know most of us learn in a very structured way, but this is how I do things, and this is how I guide people generally. There is no structure in machine learning, right? So if you're a person of structure, that A then B then C, I think you will end up dejected in life. So you look at machine learning the same way we look at life. Life itself is a mesh. So I think I would say generally speaking, I think you need to be very open and very you have to study. It's more like there's always something new that you will encounter which you don't know, and you have to be accepting of that. And it's almost like you're learning new things every day. And I would say take a time, give it a time, spend some time every day reading blogs. One of my favorite ways of learning things, and I read every day. I'm not an expert. I don't claim to be an expert because I'm learning from people better than me, like Jan Diku. He's the director of AI in Facebook. I follow the people like them. I follow people like Andrew Ng. I follow people like, let's say, Sundar Pichai, the kind of things that they comment on. Because I learned from those people. I didn't discover machine learning. I didn't discover logistic. I'm only teaching you because I learned from them. I learned from the researchers who discovered those things, right? So we all follow people. We all follow people in their respective fields who have done great work. I would say, one of the best ways to learn is from blogs. That's an excellent way to learn things. Your initial journey is more of a structured program where we are teaching you the concepts, where you're getting the initial boost. But I would say from here onwards, once you have some grounding on the conceptual level, I would say the next step is to get into Kaggle, have a parallel grounding on Kaggle. That's the whole idea why these sessions I would conduct across batches is all on Kaggle, so that people are getting a good feel. So get into Kaggle, solve a range of classification problems there, and read blogs. And one of my favorite ways to read is one thing is Twitter. I follow a lot of people on Twitter, and I'm also very active on Twitter. Like, people comment stuff, people post stuff. So that's a great way to learn, I would say. And the second thing that you can actually do is you can follow blogs like Towards Data Science. So say there are hundreds of blogs out there, but sometimes it's very hard to know what is good, what is not good. So I would say this is one of the best blogs out there in machine learning. Okay. Most of everybody else copy content. That's what it is. Okay, that's it's worthless. Okay, all these other ABCD Indian Desi platforms are all literally worthless platforms. Okay, so don't get into all that. Follow good blogs. Good blogs. Medium is a good blog. Medium.com is a good blog. Towards data science is a good blog. Reputed authors will write here, and a lot of money. The Silicon Valley backed venture capitalist backed company, so they've got a lot of money, and I think the authors are well supported here. Authors are well supported, and you will get very good quality content here. Many articles are paid, but I mean, you can. I mean, that's a small investment. That's a small investment to basically make, right? It's a small investment to make, but hey, I mean, you can always you can always take care of your cookies while accessing the site. I mean, there are ways to get around that. That will be a very different session. How to get over paywalls, but do a bit of Google searching and you will figure out how to get over paywalls. Actually, this is not only for this site, for any site. Paywalls are a very standard thing, right? See, anyway, they make a lot of money. They don't need our money. Okay, Medium is a highly rich company, so that's okay. I mean, if you're able to get over the paywalls, that's fine because you're reading it for your own learning purposes. Okay, so this is a great blog, and I will encourage you to read content from here. And you look at understanding linear regression. So there's a person who talks about linear regression, and hey, I mean, if I stumble upon it, I know everything about linear regression, but I'll still study it just to take a look at it. Hey, what has this guy done? Okay, very interesting. So correlated features. He's talking. You'll learn something. Maybe right, wrong, whatever it is, something you will learn. Right. That's the whole idea. It's all about absorbing. Okay, so very interesting. So how he has done linear ordinary least squares he talks about, and then the guy talks about quantifying the amount of variance explained. So generally, very interesting. Okay, this is very basic actually. There's nothing else done actually, honestly. See, even these kind of articles you will find, by the way. At your level, you might find it like literally worthless, not worth your time actually. Okay, so there's nothing else done actually. But I'm just saying, not all authors are like this guy. This is an open source platform, right? Maybe he also studied and just. This is also another great way to get started. I mean, you can yourself write articles. I mean, there's no such thing. You can learn some new concept. Let's say I taught you logistic today. You can probably go to Medium and write an article on your own. So it could be something as basic as what this guy wrote. But hey, I mean, that's still fine. I mean, it's still a good way to contribute, right? But that's one of the things. And then you will find some more interesting aspects. Like, is there enough space to stay? This is very interesting, like data science based thing, and you can read about it. What is the kind of stuff that this guy A/B testing in statistics? You can. So very interesting, like how Manhattan distance is being used, and a lot of math is being done here, and how they are using this to kind of figure out the distance, average distance metric. You can read about this, and probably there's some COVID-19 data sets also that are present. So this is a wonderful site I would recommend to all of you generally. Aside from that, be active in blogs, be active in Twitter, be active in LinkedIn, follow good people doing this work. Yeah, opening in incognito mode always works. Arvind might have just given out the trick, yes. But that's okay. As I said, I mean, don't feel bad for the company that's very rich. So that's okay. I think they can, it's like Google, no? I mean, you don't feel bad for Google. They're worth like $1 trillion. That's fine. I mean, yeah. Okay. How many algorithms we need to understand from industry point of view? I think that's a very broad topic. So generally all the algorithms are important, but if you talk about from a commercial industrial point of view, I would say mostly tree-based models are very, very important. I think there's a conversation we will be having shortly. I think there's a session that is planned. Tree-based models, decision tree-based models are very, very important. Very, very important. One of the most important topics out there, I would say. Yep. So aside from linear models, logistic models, if you ask me what is that one class of machine learning algorithm that is there used everywhere today as we speak, tree-based models, decision trees, and ensembles of decision trees. Broadly, the topic is called ensemble learning. Ensemble learning, I would say, are the class of algorithms that are everywhere. So whenever somebody says that, hey, I have built a machine learning model for you, I would say 99% of the time they built an ensemble model. That's the most important thing out there today. Okay, any other questions, guys? I'll be sharing the notebook with you. I know it's a little late today, but hope all of you learned something out of it. So I'll be sharing the notebook. Most of it I've already shared. The only thing that I have to share with everybody is this last part. I think this last part, I think some of you had some trouble running this code. So I'll be sharing this last part with you. So this particular piece of the code I'll be sharing with you today. Okay, yeah. Books. Books, I would say, I think I did mention this book last time, right? I interacted with all of you on the California housing. What book did I recommend that time? Hey, Narsima, you should remember. What book did I recommend last time? Let me check with the audience. What book did I recommend last time? What was the book that we? Yes, O'Reilly. What book? You should remember this, no? No, I'm asking everybody, not only one person. What exactly? Hands-on machine learning. That's the book. That's one of the best books in ML, and I will encourage you to refer to that book. Good book. Please refer to that book. Hands-on machine learning. It's a good book, and that's enough to get you started. There are two versions. I think this version you will get it for free in Google. Google it out. This version you will get it for free, and this version is the more I think this is not yet available for free. So you got it both, okay? You bought it or okay? Okay, good. Okay, how come you got this link? That's very interesting. Okay, this is supposed to be an updated edition. Okay, good. All right, you can share with your colleagues. Yeah. Okay. Okay, that's good. Oh, that's interesting because when you do Google search, you actually get the first link. I think the second link might be hidden somewhere. We need to figure it out. Discussion forums link, is it? Okay. Okay. Right. All right. Okay. So how to crack hackathons, Gaurav? There's no one question I would have for you on that, but it's more about practice. You know, I mean, so you need to be getting into the groove of things, right? So hackathon is not like one fine day we wake up and we say, okay, let's go to a hackathon. I mean, that's not how it happens. Hackathons are again more like getting into the groove. Now we are actually getting into the groove. We are doing casual every day. So now we are like, okay, now we are confident. That's how it starts. Okay, that's how it starts. And I mean, so after a while, it feels like, okay, see, next time I ask you to go to Kaggle, first time all of you struggled. Okay, what is notebook? What is URL? And that is obvious. Even when it was my first day, I also struggled. Okay, that's obvious. But next time you do it, you're like, okay, it's 10 seconds, it's up and running. That's it. That's learning. That's how the human mind learns. So hackathons are no rocket science. It's the same way that you do it there. So these are also like hackathons that we're discussing. So you participate in one competition, you do well, and then it becomes a practice for you. So I would say it's just about being involved and being participating. So start with some competitions and don't solve it for accuracy sake, but I would say at least be involved in it. Maybe you can look at some past competitions and you learn a lot from that. At least you will learn from other people's solutions, how other people do it. You will learn best practices from that. But hackathons are not like a sure short way of success. Success is not just doing well in hackathons, because see, doing well in hackathons is like fitting an XG boost and getting the highest accuracy. That doesn't make any sense. Most people, like, they know nothing. Okay, I mean, I'm not saying everybody is like that, but mostly people are like, okay, they'll copy paste some code from somewhere. Like, you don't even know what is happening, why it's happening. What is p value? I don't even care. They just go and plug it in A B C D E. That's what we call jugaad in India, right? Do some jugaad and you get it working. Okay, and you reach the top 5%. I mean, so hackathon is cracking it is not the should be does not be the only intent. The intent should be to learn in the process. Cracking a hackathon is not the only intent, by the way. Right. Chalo, guys, it's been a long session. I think I'll not hold you back any further. I think tomorrow is a Monday. So I wish you a good week ahead. I think we'll be interacting again. Just to clarify, we'll be having one more class specifically for logistic. Okay, so I'll interact with my team as well. We'll schedule one more session, and that session will be going over to the entire regularization aspect, not only for logistic, because see, logistic regularization, although the title is that way, but regularization is a generic concept actually. It is applicable for all linear models actually. Okay, it's basically a generic concept. So we'll be having a detailed session on that, so don't worry. So we'll schedule it probably sometime next weekend or next to next weekend. Over a weekend we can actually do it, and yeah. Okay. Okay. Yeah. Long session. Thank you for staying back, all of you. So take care, everybody. Take care. Any other questions anybody has right now? Okay. Everybody would have left now. Okay, good. I think we are interacting shortly again for boosting session probably. So yeah. Oh, you want to stay back again? Okay, no, we cannot stay back any further. Yeah. Have you read the second chapter? Second chapter is a good chapter actually. But have you read it? If you should definitely read it, I would say. You should definitely read the second chapter. Okay. So I will ensure that I share this particular notebook with all of you. Okay. Chalo, take care all of you. I'll see you everybody. Yeah, bye bye.